Hello there, and welcome to Physics with William, where curiosity settles in, difficult ideas are given plenty of room, and science takes the quieter road towards sleep. Tonight we are stepping into one of the biggest problems in all of physics. It is a problem that has resisted some of the brightest minds for more than a century. It sits at the point where our best description of gravity meets our best description of the smallest things in nature. Both descriptions work extremely well on their own. Put them together though, and the conversation becomes awkward very quickly. The problem is called quantum gravity. The name sounds as though someone simply placed two scientific words next to each other and hoped for the best. In a way, that is not entirely wrong. Quantum refers to the rules that govern particles, atoms, and events at very small scales. Gravity refers to the attraction that shapes planets, stars, galaxies, and the structure of the universe. Quantum gravity is the attempt to understand gravity using the principles of quantum physics. That sounds simple enough until we remember that gravity is not treated like an ordinary force in our current theories. It is described as the bending of space and time themselves. Asking for a quantum theory of gravity therefore means asking what space and time are made of, how they behave at the smallest possible level, and whether the smooth universe we experience is smooth at all. Before we go further, let me ask you something. Where are you listening from tonight, and what does the room around you look like right now? Perhaps you're in bed with the lights low. Perhaps you're on a sofa with a cup of tea nearby. Maybe you are listening while working, travelling, or trying to persuade your thoughts to slow down for the evening. Wherever you are, gravity is keeping you there. It is holding you to the floor, guiding the air around you, and keeping the Earth moving around the Sun. At the same time, the atoms in your body are following quantum rules that are very different from the rules we use to describe planets and stars. You're living inside both worlds at once, even though physics still does not know how those worlds fit together. If you find this kind of slow scientific journey soothing, interesting, or useful for winding down, you can give the video a like and subscribe to the channel. It helps this quiet corner of science reach other people who may also enjoy learning why the universe is so difficult to organise. There is no need to stay sharply focused on every detail. Let the ideas arrive at their own pace. Quantum gravity has waited a very long time to be understood, so it can certainly wait while you get comfortable. To see why this problem matters, it helps to notice how successful modern physics already is. Scientists have built theories that can predict the motion of planets, the behaviour of light, the structure of atoms, the life cycles of stars, and the expansion of the universe. These theories are not vague guesses. They have survived careful experiments and have allowed us to build technologies that would have looked impossible only a few generations ago. Satellites, computers, medical scanners, lasers, and modern communication all depend on physical theories that describe nature with remarkable accuracy. The trouble is that physics does not currently have one complete set of rules for everything. Instead, it has two major frameworks. One deals mainly with gravity and the large-scale structure of the universe. The other deals mainly with particles and the small-scale structure of matter. The first is general relativity. The second is quantum mechanics, together with the more advanced quantum field theories built from it. Each framework is excellent in the situations for which it was designed. General relativity can describe the orbit of a planet, the bending of light around a star, and the collapse of matter into a black hole. Quantum theory can describe electrons, atoms, radiation, and the strange probabilities that appear in the microscopic world. Most of the time, this division causes no practical difficulty. If an engineer is calculating the path of a satellite, quantum uncertainty is not the main concern. If a physicist is studying an electron inside an atom, the gravity of that electron is so weak that it can usually be ignored. Nature allows us to use the right theory for the right job, rather like using a map of a city for driving and a floor plan for finding the bathroom. Both can be accurate without needing to show the same details. Certain places in the universe do not respect this convenient separation. In those places, gravity becomes extremely strong while matter is compressed into an extremely small region. A black hole is the most famous example. Near the centre of a black hole, our equation suggests that density and curvature become unlimited. Physicists call this a singularity, although the word may be less a description of a real object and more a warning that the theory has reached the edge of its ability. The mathematics is effectively saying that something important is missing. The beginning of the universe presents a similar problem. If we run the history of cosmic expansion backward, matter and energy become hotter, denser, and more tightly packed. Eventually we reach conditions where both quantum effects and gravity should be important at the same time. General relativity can describe an expanding universe, and quantum theory can describe matter and radiation, but neither can fully explain the earliest moment using the current rules. This is one reason quantum gravity is not a decorative extra for theoretical physicists. It may be necessary for understanding how the universe began. There is also a deeper reason. Physics aims to describe nature in a consistent way. When two successful theories produce incompatible ideas about the same situation, that is a sign that our understanding is incomplete. General relativity treats space and time as a smooth structure that can curve. Quantum theory treats physical quantities as uncertain, fluctuating, and often divided into discrete outcomes. One theory gives us a continuous stage. The other tells us that everything on the stage behaves in restless and probabilistic ways. When gravity becomes quantum, the stage may have to join the performance. This creates questions that sound simple until we try to answer them. Can space come in tiny pieces? Can time fluctuate? Is there a smallest possible distance? Does gravity have a particle associated with it? Are black holes destroying information, hiding it, or returning it in some altered form? What happens at the centre of a black hole if there is no true singularity? What existed during the earliest meaningful instant of the universe? These are not separate curiosities placed in a list for dramatic effect. They are connected expressions of the same missing theory. The phrase "greatest unsolved problem" can be used too easily, especially in science, where many problems are large enough to ruin a perfectly peaceful afternoon. Quantum gravity earns the description because it touches the foundations of several fields at once. It challenges our ideas about matter, space, time, information, and cause and effect. Solving it may require new mathematics, new experiments, and perhaps a new way of deciding what counts as fundamental. It is worth being clear about what unsolved means here. Physicists do have serious candidate theories. They are not staring at an empty page. String theory proposes that the basic objects of nature are tiny extended strings rather than point-like particles. Loop quantum gravity suggests that space itself may have a discrete structure built from networks of quantum relationships. Other approaches explore ideas involving causal sets, emergent spacetime, holography, modified quantum principles, and new forms of geometry. Some researchers focus on black holes, others study the early universe. Still others look for tiny experimental signals that might reveal whether gravity behaves quantum mechanically. None of these approaches has yet received decisive experimental confirmation. That is the main difficulty. A theory may be mathematically elegant and internally consistent, but physics eventually asks nature to decide. Quantum gravity effects are expected to become obvious only at scales far smaller than anything we can directly reach with current particle accelerators. The energies involved are enormous. Building a machine powerful enough to probe those scales directly would be far beyond present engineering. It would also make local planning permission rather complicated. Because direct access is difficult, researchers look for indirect clues. They study black hole radiation, gravitational waves, the behavior of matter near extreme objects, patterns in the early universe, and the possibility that quantum gravity could leave faint traces in high-energy particles travelling across space. They also examine logical tensions within existing theories. Sometimes progress begins not with a new observation, but with the realization that two accepted ideas cannot both remain unchanged. One such tension involves information. In quantum physics, information about a system is not supposed to vanish. It can become scrambled, spread out, or extremely difficult to recover, but the basic rules preserve it. Black holes, however, appear to swallow matter and later lose mass through a very slow process known as Hawking radiation. If the black hole eventually disappears, and the outgoing radiation contains no record of what fell in, information seems to be lost. That would challenge a central principle of quantum theory. If the information does escape, we need to understand how. The debate has led to some of the most important ideas in modern theoretical physics, including the possibility that a region of space can be described by information stored on its boundary. Another tension concerns the meaning of time. In ordinary quantum theory, time is usually treated as a background parameter. The state of a system changes as time passes. In general relativity, time is part of the physical system. It can stretch, slow, and respond to matter and energy. Once we try to make gravity quantum, we no longer have a simple external clock standing safely outside the universe. The clock is part of the universe too. This is sometimes called the problem of time, and it forces physicists to ask how change can be described when time itself is one of the things that must be explained. That question may feel remote from daily life, but daily life already hides several assumptions about time. We assume events happen in an order. We assume causes come before effects. We assume clocks can be compared. We assume the present is different from the past. General relativity complicates some of these ideas, and quantum theory complicates others. A complete theory may show that time is not fundamental in the way we imagine. It could emerge from relationships between physical systems, much as temperature emerges from the motion of many particles. An individual particle does not carry a tiny thermometer, yet a large collection of particles can have a temperature. Time may be similar, although the details remain uncertain. Space may also be emergent. We usually think of distance as one of the basic facts of the world. Two objects are either close together or far apart. Some approaches to quantum gravity suggest that spatial relationships could arise from a deeper network of quantum information. In that picture, space is not the container in which things exist. It is a large-scale result of how more basic elements are connected. The familiar world would then resemble an image on a screen. It appears smooth from a normal distance, but its smoothness depends on smaller units and relationships that are not obvious to the eye. This does not mean the universe is literally a computer screen, nor does it mean we're required to add the word quantum to every ordinary object before breakfast. Analogies help us approach unfamiliar ideas, but they have limits. Quantum gravity is difficult partly because our everyday intuition developed in a world of moderate speeds, weak gravity, and objects much larger than atoms. We are well prepared to judge whether a chair will support us. We are less naturally prepared to imagine a state in which geometry itself has no definite form. Even the word gravity can mislead us because gravity feels so familiar. It keeps cups on tables and rain moving toward the ground. In general relativity, though, gravity is not simply a pulling force travelling through space. Matter and energy change the geometry of space and time, and objects move within that geometry. The Earth follows a path around the Sun because the Sun changes the structure around it. A falling object follows the straightest available path through curved spacetime. This description has been tested with extraordinary precision. Quantum theory is equally successful and even less intuitive. It tells us that particles can behave like waves, that outcomes are described through probabilities, and that systems can become linked in ways that do not resemble ordinary mechanical connections. Quantum effects are not signs that instruments are poor or scientists are confused. They are built into nature. Repeated experiments have confirmed them to astonishing accuracy. The conflict appears because the two frameworks begin from different assumptions. General relativity uses a dynamic geometry. Quantum theory normally needs a background against which events are defined. General relativity is smooth and continuous. Quantum theory is filled with fluctuations. General relativity describes gravity through curvature. Quantum field theory describes other forces through fields and particles acting within spacetime. Applying the usual quantum methods to gravity produces mathematical infinities that cannot be handled in the same successful way used for the other forces. Infinities in a calculation are not always fatal. Physicists have developed methods for reorganizing theories so that meaningless infinite results are replaced by finite predictions. This procedure works extremely well for the electromagnetic force and the nuclear forces. Gravity resists the standard treatment. The higher the energies involved, the more new infinities appear, and the theory loses predictive control. It can still be used as an effective approximation at ordinary energies, but it does not provide a complete description at the deepest level. The phrase effective approximation is important. It does not mean general relativity is wrong. Newtonian gravity is also an approximation, yet it remains useful for many tasks. Engineers do not need to solve Einstein's equations to design every bridge. A newer theory usually does not throw the older one away. It explains why the older theory works and shows where its limits are. Quantum gravity should reduce to general relativity in situations where space-time is large and smooth. It should also agree with quantum theory where gravity is weak. The missing theory must contain the success of both without keeping their contradiction. That is a demanding task. It is also what makes the search so interesting. We are not merely looking for another particle to add to a table or another correction to a known calculation. We may be looking for the principles from which space, time, matter, and gravity all arise. The eventual answer could be surprisingly conservative, extending familiar ideas with careful changes. It could also be so different from current thinking that future students will wonder why anyone expected space and time to be fundamental in the first place. For now, no one knows which path is correct. That uncertainty is not a weakness of science. It is the honest condition of being near the edge of knowledge. Researchers disagree, revise their ideas, build new models, and search for observations capable of separating one possibility from another. Progress can be slow because the problem is genuinely difficult, not because nothing is happening. Each result narrows the field. Each failed proposal shows what a successful theory must avoid. Even disagreements can clarify the question. Tonight we will move through this problem carefully. We will look at why general relativity and quantum theory are both so successful, where their assumptions clash, why black holes are central to the discussion, and what the leading approaches are trying to accomplish. We will also consider how a theory can be judged when direct experiments are difficult, what clues might be available, and why the answer matters beyond a small group of specialists. There is no need to memorize names or hold every concept in perfect detail. The central idea is enough for the moment. Physics has two powerful descriptions of nature. One explains gravity by changing the geometry of space and time. The other explains the microscopic world through quantum states, probabilities, and fields. Both are supported by evidence. Both are incomplete when extreme gravity and quantum effects appear together. That meeting point is where quantum gravity begins. It is not a single object waiting to be found in a laboratory drawer. It is the effort to discover a common language for two theories that currently speak past each other. To understand why their disagreement has lasted so long, we first need to meet them separately, see what each one does so well, and notice the assumptions they carry into the conversation. The first of these theories is general relativity, Albert Einstein's description of gravity. The second is quantum mechanics, the framework used to describe matter and energy at very small scales. It is tempting to imagine that they disagree because one of them must be wrong. That would make the situation much easier. We could test them, discard the loser, and return to our tea. The real difficulty is that both theories have been tested again and again, and both have passed with extraordinary success. General relativity is used when gravity matters and when large objects are involved. It explains how planets orbit stars, how light bends near massive bodies, how the universe expands, and how black holes can form. Quantum mechanics is used when atoms, particles, and microscopic processes matter. It explains why atoms are stable, how light interacts with matter, why chemicals behave as they do, and how modern electronics work. Every time a phone processes information, every time a laser produces a narrow beam, and every time a medical scanner detects signals from the body, quantum rules are quietly doing their job. There is nothing unusual about having different theories for different situations. A map of a country and a map of a building serve different purposes. One shows roads, cities, and borders. The other shows rooms, doors, and staircases. No one complains that the national map has failed because it does not include the cupboard under the stairs. Physics often works in the same way. A theory can be accurate within a certain range without describing every level of reality. The problem begins when the ranges overlap. Most objects do not force gravity and quantum effects to become equally important. A tennis ball is large enough that its quantum behavior is impossible to notice in ordinary conditions. An electron is small enough that its own gravity is almost completely irrelevant. This separation allows physicists to use general relativity for one class of problems and quantum mechanics for another. Nature has kindly placed many everyday situations in the comfortable middle. Black holes are not in that comfortable middle. Neither is the earliest stage of the universe. In those settings, enormous amounts of matter and energy can be concentrated into extremely small regions. Gravity becomes intense, but the scale also becomes small enough that quantum effects cannot be ignored. The two theories are then asked to describe the same event. That is when their differences stop being a philosophical inconvenience and become a direct scientific problem. To understand the disagreement, it helps to look at what each theory assumes about the world. General relativity treats space and time as parts of one physical structure called spacetime. This structure is smooth. It can bend, stretch, and change shape, but it is still described as continuous. Matter and energy affect its geometry, and that geometry affects how matter moves. A planet orbiting a star is not being pulled across an empty stage by an invisible rope. It is moving through curved space-time, following the natural path created by the star's mass. Quantum mechanics begins from a very different picture. At small scales, physical properties are not always definite before they are measured. A particle can be described by a range of possible positions, possible motions, or possible outcomes. These possibilities are not merely signs that we lack information. They are built into the theory itself. Quantum mechanics does not usually say that a particle has one hidden position and that we simply have not found it yet. It gives probabilities for what may be observed. That probabilistic structure is one reason the quantum world seems so strange. In daily life, we expect objects to be somewhere. A book is on the table, in the drawer, or in the hands of someone who has forgotten to return it. Quantum objects do not always fit that expectation. Before a measurement, a particle may need to be described as a combination of several possibilities. When an observation is made, one result appears. The theory predicts the likelihood of each result with remarkable precision, even though it cannot always tell us which individual result will occur. General relativity does not normally work that way. It describes a definite geometry. Given the right information about matter and energy, the theory determines how space-time curves and how objects move. Quantum mechanics describes uncertainty and fluctuations. General relativity describes a smooth structure. One theory is built around fixed geometric relationships. The other allows multiple possible states to exist in the description at once. This difference becomes serious when we ask a simple question. What happens if the geometry of space-time must also obey quantum rules? If matter can exist in a combination of possible states, and matter determines the shape of space-time, then space-time may also need to exist in a combination of possible shapes. The distance between 2 points might not have one definite value. The order of events might become uncertain. Even the meaning of before and after could become less clear. Physicists are not troubled by unusual ideas merely because they are unusual. Science has survived many surprises. The Earth moves. Time slows with speed. Light behaves as both a wave and a particle. The real test is whether an idea can be expressed consistently, and whether it leads to predictions that can be checked. Quantum gravity is difficult because the standard methods that work for other forces do not produce a complete and manageable theory of gravity. In quantum field theory, forces are described through fields that fill space. Particles can be understood as excitations of those fields. The electromagnetic field, for example, has quantum excitations associated with particles of light. Similar methods describe the forces acting inside atomic nuclei. These theories contain calculations that can produce infinite quantities, which sounds like a sign that everyone should close the notebook and go home. Instead, physicists developed a careful procedure for reorganizing the calculations so that the infinities can be absorbed into quantities that are measured experimentally. The remaining predictions are finite and extremely accurate. When the same strategy is applied directly to gravity, the problem becomes worse. More and more infinities appear as calculations become more detailed. They cannot all be handled using a limited set of measured quantities. The theory loses the ability to make clear predictions at very high energies. This does not mean quantum calculations involving gravity are always useless. At low energies, gravity can be treated as an effective quantum theory, and meaningful results can be obtained. The trouble appears when we demand a complete description that remains valid at the smallest distances and highest energies. One way to picture the issue is to imagine examining a smooth road from farther away. At normal distance, the surface looks continuous. Move closer, and small stones, cracks, and grains become visible. General relativity describes spacetime as though the road remains smooth no matter how closely we inspect it. Quantum theory suggests that anything physical should show fluctuations when examined at sufficiently small scales. If spacetime itself fluctuates, the road may stop looking like a road at all. It may become a rapidly changing structure for which ordinary distance and direction no longer work in the usual way. The scale at which this is expected to matter is extraordinarily small. It is far smaller than an atom, and far smaller than the particles inside an atom. Current experiments cannot directly examine spacetime at that level. Even our most powerful particle accelerators operate at energies that are tiny compared with those thought necessary for obvious quantum gravity effects. This experimental distance gives theorists room to explore many possibilities, but it also makes it difficult to determine which possibility nature has chosen. The disagreement also involves the role of time. In ordinary quantum mechanics, time usually sits outside the system being studied. A physicist describes how a quantum state changes as time passes. The clock is treated as a reliable background device. General relativity does not allow such a simple arrangement. Time is part of spacetime, and spacetime is affected by gravity. A clock near a massive object runs at a different rate from a clock farther away. A moving clock runs at a different rate from one at rest relative to an observer. There is no single universal clock that stands outside everything else. Combining the theories means treating the clock itself as a quantum object and treating time as part of a changing quantum geometry. Then the usual question: how does the system change with time becomes difficult because the thing used to measure change is included inside the system. It is rather like asking someone to measure the length of a ruler using only that same ruler, while the ruler changes size during the measurement. The task may still be possible, but the ordinary method is no longer enough. This is known as the problem of time, though it is really a collection of related problems. Some approaches suggest that time is not fundamental. Instead, time may arise from relationships between parts of the universe. One system can act as a clock for another. Change is then described by comparing physical processes rather than referring to an external time that exists independently. This view is still being developed, and different theories implement it in different ways. Causality creates another difficulty. In ordinary reasoning, a cause happens before its effect. General relativity usually preserves this order locally, although extreme geometries can produce unusual possibilities. Quantum theory allows correlations between distant systems that cannot be explained by ordinary local mechanisms, though these correlations do not allow usable signals to travel faster than light. A theory of quantum gravity must preserve enough causal structure to avoid contradictions, while also allowing space-time itself to fluctuate. Black holes bring many of these tensions together. General relativity predicts that when enough matter collapses into a small region, an event horizon can form. This horizon marks a boundary beyond which nothing can return to the outside, at least according to the classical theory. The black hole can be described using only a few overall properties, while the detailed information about the matter that formed it appears to become inaccessible. Quantum theory adds a surprising result. Black holes are not completely black. They can emit a faint form of thermal radiation and gradually lose mass. Over an immense period, a black hole may evaporate. If it disappears entirely, physicists must ask what happened to the information carried by everything that fell inside. Quantum mechanics says that information should be preserved. A simple reading of black hole evaporation suggests that it may be destroyed. This conflict is called the black hole information problem. It has occupied physicists for decades, because it is not merely about missing records. Information preservation is tied to the basic consistency of quantum theory. If information can truly disappear, then the standard rules of quantum mechanics may need to change. If it does not disappear, then our description of black holes or space-time must be incomplete. Several possible answers have been proposed. Information might escape in subtle correlations within the radiation. It might be stored in a way associated with the horizon. The interior of the black hole might not have the structure predicted by classical relativity. Space-time itself might emerge from deeper quantum information, making the usual distinction between inside and outside less fundamental than it appears. Each proposal solves some problems and creates others. The early universe creates a related test. General relativity describes cosmic expansion very well after the universe has already reached a certain state. If the equations are pushed backward, density and temperature rise until the classical description approaches a singular beginning. At that point, the theory no longer provides a sensible account. Quantum effects should become dominant, but ordinary quantum theory assumes a space-time background on which those effects occur. At the beginning, that background is exactly what needs to be explained. A successful theory of quantum gravity could replace the singular beginning with a different process. The universe might have passed through an earlier phase. Space could have emerged from a quantum state. A collapse might have been followed by a bounce. There may have been no first instant in the ordinary sense because time itself could have developed along with the universe. These suggestions remain under investigation. The important point is that the current theories do not supply a complete answer. Despite their conflict, general relativity and quantum theory are not enemies in every calculation. Physicists often use them together in approximate ways. Quantum fields can be studied on a curved but classical spacetime. This method led to the prediction of black hole radiation. Gravitational effects can also be included as small corrections in quantum calculations at low energy. The trouble comes when the quantum behavior of spacetime itself cannot be ignored. The situation resembles two expert guides who agree across most of a long journey, but provide incompatible instructions at the final crossing. One guide knows every large road, bridge and mountain. The other understands every small step, loose stone and change in footing. For most of the route, each can be consulted separately. At the narrowest and most dangerous point, both are needed, yet they disagree about what the ground is made of. It is easy to assume that a single final theory must look like a direct combination of the two. History suggests otherwise. When older ideas are united, the result often changes the meaning of both. The theory of electromagnetism did not merely place electricity and magnetism side by side. It showed that they are aspects of one field. Relativity did not simply adjust Newton's laws. It changed the understanding of space, time, and gravity. Quantum gravity may require a similar shift. Perhaps space-time is not fundamental. Perhaps particles are not fundamental either. Both may arise from a deeper structure. Some theories place extended objects at the foundation. Others use networks, loops, causal relationships, or quantum information. The names differ because researchers are trying different starting points. No approach has yet received decisive experimental support. This lack of confirmation can make the subject seem unusually speculative. There is speculation, but it is constrained by difficult requirements. Any successful theory must agree with general relativity where gravity is classical. It must agree with quantum physics where gravity is weak. It must provide a sensible account of black holes and the early universe. It must avoid uncontrolled infinities. It should preserve observed causal behavior and explain why spacetime appears smooth at ordinary scales. Meeting all of these requirements at once is far harder than inventing an interesting model. Many ideas work in one limited setting, but fail elsewhere. Some are mathematically consistent but difficult to connect with experiments. Others offer testable suggestions but do not yet provide a complete framework. Progress involves checking each proposal against everything physics already knows, which is a demanding list. There is also the practical problem of evidence. The strongest quantum gravity effects may occur at scales that cannot be reached directly. Researchers therefore search for indirect signs. They study the radiation from black holes, the structure of gravitational waves, high-energy particles from space, and patterns left over from the early universe. They design laboratory experiments that might detect whether gravity can create quantum entanglement between small masses. Even a modest signal could establish that gravity itself has quantum behavior. Such experiments are extremely difficult because gravity is weak compared with the other forces. A small object feels electromagnetic effects from its surroundings far more strongly than it feels the gravity of another small object. Vibrations, heat, stray electric fields, and background noise can overwhelm the signal. The experiment must isolate delicate quantum systems while measuring a gravitational interaction that is almost unbelievably faint. It is the scientific equivalent of trying to hear a quiet conversation while standing beside a washing machine full of cutlery. Still, the effort matters. A direct demonstration that gravity can carry quantum information would not produce a full theory, but it would rule out certain alternatives and guide future work. Physics often advances through small pieces of evidence rather than one dramatic revelation. A slight deviation, a missing pattern, or an unexpected correlation can show which direction is worth following. For now, the two great theories continue to share the universe without sharing a common foundation. General relativity describes the large-scale structure with precision. Quantum mechanics describes the microscopic world with equal success. Their disagreement appears only in extreme conditions, but those conditions include the birth of the universe, the interior of black holes, and the deepest structure of space and time. The next step is to understand gravity on its own terms. Before asking how it might become quantum, we need to see why Einstein's description was such a major change, why curved space-time replaced the older idea of a simple pulling force, and why a theory that works so beautifully can still point toward its own limits. To understand why gravity causes so much trouble for quantum physics, we first need to understand what gravity became in the hands of Albert Einstein. Before Einstein, the most successful description came from Isaac Newton. Newton treated gravity as a force acting between objects with mass. The Earth pulls on the moon. The sun pulls on the Earth. The Earth pulls on you, your bed, your cup of tea, and the biscuit that somehow always lands on the floor with the most disappointing side facing downward. Newton's theory worked remarkably well. It could predict the paths of planets, explain the tides, describe falling objects, and guide spacecraft through the solar system. It remains useful today because, in ordinary conditions, it gives answers that are accurate enough for a great many purposes. If you want to calculate the path of a ball, the motion of a bridge component, or the orbit of a satellite that is not too close to an extreme gravitational object, Newton's picture is often entirely sufficient. There was, however, a question hidden inside it. How did gravity travel from one object to another? In Newton's description, the sun could influence the Earth across the enormous distance between them. The force appeared to act through empty space. Newton himself was uncomfortable with the idea that one object could affect another instantly, without some physical mechanism carrying the influence. His mathematics described what gravity did, but it did not fully explain what gravity was. That problem became more serious after scientists learned that light has a fixed speed. If no influence can travel faster than light, gravity could not act instantaneously across space. Suppose the sun vanished, which is not scheduled and would be extremely inconvenient. In Newton's picture, the Earth might respond immediately because the gravitational pull would disappear at once. According to relativity, the change could not reach us instantly. It would take about 8 minutes, the same amount of time sunlight takes to travel from the sun to the Earth. Einstein needed a new description, one in which gravity did not operate as an invisible command sent instantly between distant masses. His solution changed the meaning of space and time. The first step came with special relativity. Einstein showed that space and time are closely connected. Observers moving at different speeds may disagree about distances, durations, and whether two events occurred at the same time. Time is not universal. There is no single clock that measures the same passing seconds for everyone throughout the universe. Space is not an unchanging container either. Measurements of length depend on motion. This was already a major shift, but special relativity did not include gravity. Einstein then spent years trying to extend the theory. One of his most important insights began with a simple comparison between gravity and acceleration. Imagine that you are inside a closed lift with no windows. The lift is standing on the surface of the Earth. You feel your feet pressed against the floor because the floor prevents you from falling toward the center of the planet. Now imagine that the lift is far from any planet or star, floating in empty space. A rocket attached beneath it accelerates upward. The floor pushes against your feet, and objects released from your hand fall toward the floor. From inside the lift, the two situations can feel the same. You might be standing in a gravitational field, or you might be accelerating through space. Without looking outside, it may be impossible to distinguish them through a small local experiment. Einstein took this equivalence seriously. Gravity and acceleration were not merely similar. Their relationship pointed toward a new understanding of motion. If acceleration can imitate gravity, then perhaps gravity is not an ordinary force at all. Consider another lift, this time falling freely toward the Earth. A person inside releases a small object. The person and the object fall together at the same rate, so the object appears to float beside them. For a brief period, the person feels weightless. Gravity has not disappeared. The lift, the person, and the object are all moving under its influence. Yet inside the falling lift, there is no local sensation of a gravitational force. Astronauts in orbit experience something similar. They are not beyond Earth's gravity. In fact, gravity at the height of the International Space Station is still quite strong. The astronauts feel weightless because the station and everything inside it are continuously falling around the Earth. Their sideways motion is fast enough that they keep missing the ground. Orbit is therefore a very successful form of falling. These observations suggested that what we call gravity might be connected to the paths objects naturally follow when nothing is pushing against them. A person standing on the ground does not feel gravity, because some mysterious force is pulling in the ordinary sense. The person feels the ground pushing upward, preventing the natural free fall that curved space-time would otherwise produce. This is where the geometry enters. In general relativity, space and time form a combined structure called spacetime. Matter and energy change the geometry of that structure. Objects then move along the most direct paths available within the curved geometry. The sun changes space-time around it, and the Earth follows a path through that curved region. The Earth changes space-time too, and the Moon follows its own path in response. The common image is a heavy ball placed on a stretched rubber sheet. The ball creates a dip, and smaller balls roll around it. This analogy is useful, but it also has limitations. The rubber sheet bends because gravity pulls the ball downward, so it uses gravity to explain gravity. Actual space-time does not need to bend into some larger external space. Its internal geometry changes. Distances, durations, and the paths between events are altered. The bending also involves time, not only space. This is essential. A picture showing a curved surface can make gravity look like a purely spatial effect, but changes in the passage of time are a major part of how gravity works. A clock closer to a massive object runs more slowly than a clock farther away. The difference is usually tiny, but it is measurable. Place one extremely accurate clock on the ground and another at a higher altitude, and they will not remain perfectly synchronized. The lower clock, sitting deeper in Earth's gravitational field, will run slightly more slowly. Even a small difference in height can produce a detectable effect if the clocks are precise enough. This means that your feet and your head do not move through time at exactly the same rate. Your head is slightly farther from the centre of the Earth, so it ages a little faster. The difference is far too small to explain why your shoes seem older than the rest of you, but the effect is real. Gravitational time dilation is not an optional detail added to make relativity more interesting. It affects technology. Satellites used for global positioning carry precise clocks. Those satellites are farther from Earth, where gravity is weaker, so their clocks run faster than clocks on the ground. They're also moving quickly, which causes a different relativistic effect that slows them down. Both corrections must be included. Without them, location errors would grow rapidly, and a navigation system could place you far from the road you're actually using. This would be especially unhelpful near a roundabout. Light also responds to curved space-time. A beam passing near a massive object follows the geometry around it, so its path appears bent. During a solar eclipse in the early 20th century, astronomers measured the apparent positions of stars near the Sun. Their light had been deflected as Einstein's theory predicted. The result helped make general relativity famous. We now observe this effect throughout the universe. Galaxies and clusters of galaxies can bend light from objects behind them. This is called gravitational lensing. Sometimes the background object appears stretched into arcs. Sometimes several images of the same distant source appear around the foreground mass. Under the right conditions, the light can form a ring. Gravitational lensing is more than an impressive visual effect. It allows astronomers to map matter that cannot be seen directly. The amount of bending reveals how mass is distributed, including forms of matter that do not emit light. It can also magnify extremely distant galaxies, allowing telescopes to observe objects that might otherwise be too faint. General relativity made another prediction that seemed unusual at first. Changes in the distribution of mass can produce waves in space-time. If massive objects accelerate in the right way, they create disturbances that travel outward at the speed of light. These are gravitational waves. Two black holes orbiting each other provide a powerful example. As they circle, they lose energy through gravitational radiation. Their orbit shrinks, their speed increases, and eventually they merge. The final moments send a strong wave through the surrounding universe. By the time it reaches Earth, the disturbance is incredibly small, but modern detectors can measure it. The first direct detection of gravitational waves came from a merger of black holes more than 1 billion light-years away. The detectors measured tiny changes in distance as the wave passed. The shift was much smaller than the width of an atomic nucleus. Extracting that signal required extraordinary control of vibration, temperature, and background noise. A passing vehicle, a small ground movement, or an enthusiastic bird near the equipment could be more obvious than the event being measured. The detection confirmed a prediction made many decades earlier and opened a new way to observe the universe. Traditional telescopes gather light. Gravitational wave observatories detect motion in space-time itself. They can study collisions that may produce little or no visible light, including mergers between black holes. Black holes are perhaps the most extreme demonstration of curved space-time. When a sufficiently massive star exhausts its fuel, it may no longer support itself against collapse. If enough mass is compressed into a small enough region, an event horizon forms. Beyond that boundary, every future directed path leads farther inward. Escaping would require moving faster than light, which relativity does not allow. It is common to describe a black hole as having such strong gravity that not even light can escape. That is correct, but it can sound as though the black hole is simply a very powerful version of an ordinary gravitational pull. General relativity gives a more precise picture. The geometry inside the event horizon is arranged so that moving toward the centre is as unavoidable as moving toward tomorrow. The interior is not merely a place where escape is difficult. The structure of space-time removes the outward route from the available future. A person falling into a large black hole might cross the event horizon without noticing an immediate local boundary. There is no solid surface there. No sign needs to announce that returning is now impossible. A distant observer, however, would see the falling person slow and fade as light from them becomes increasingly stretched and delayed. This difference between viewpoints is not a mistake. Relativity often allows observers in different conditions to describe events differently, while agreeing on the underlying physical rules. The falling observer crosses the horizon in a finite amount of personal time. The distant observer never sees the crossing completed in the ordinary way. Light from the falling object becomes weaker and redder until it effectively disappears. Closer to the centre, tidal effects become severe. Gravity is stronger on the part of an object nearest the centre than on the part farther away. This difference stretches the object lengthwise and compresses it sideways. The process has acquired the memorable name spaghettification, proving that even very serious physics sometimes sounds as though it was named shortly before dinner. For a small black hole, these tidal forces can become deadly before the horizon is crossed. For a supermassive black hole, the horizon can be so large that the local tidal effects there are modest. A falling traveller might pass through safely at first, although the later part of the journey remains firmly outside the range of recommended tourism. At the centre, classical general relativity predicts a singularity. Quantities such as density and space-time curvature grow without limit. The familiar laws stop providing meaningful answers. This is often described as a point of infinite density, but physicists are cautious about taking that image too literally. An infinity in a theory can indicate that the theory is being pushed beyond the region where it applies. General relativity may be giving a warning rather than a description. It may be saying that quantum effects ignored in the classical theory have become essential. The singularity is therefore one of the strongest reasons to seek quantum gravity. A more complete theory might replace it with a finite quantum state, a new geometric phase, or something that cannot be described using ordinary space and time. The beginning of the universe leads to the same difficulty. General relativity tells us that the universe has expanded from a much hotter and denser state. It describes the expansion with great success over most of cosmic history. Observations of distant galaxies, background radiation, and the distribution of matter support this broad picture. If the equations are followed backward, the universe becomes denser until the description reaches another singularity. Once again, the result does not necessarily mean that the universe began as a literal point containing infinite density. It may mean the classical theory cannot describe the earliest conditions. At that stage, gravity was strong, the relevant scales were tiny, and quantum behavior should have mattered. The same theory that explains planets, gravitational lenses, expanding space, and black hole mergers therefore points toward places where it cannot finish the job. This is not unusual in science. A powerful theory can contain clues about its own limits. Newtonian gravity predicted many motions accurately, but it could not account for every detail of Mercury's orbit. General relativity explained the difference. Classical physics described heat and light in many situations, but certain observations required quantum theory. General relativity may occupy a similar position. It is not likely to be discarded. A theory of quantum gravity must explain why general relativity works so well across large distances and moderate curvatures. Einstein's geometry should emerge as the large-scale behavior of the deeper theory, just as the smooth surface of water emerges from a huge number of molecules. This idea of emergence may be central. Space-time looks continuous to us, but that does not prove it remains continuous at every scale. A sheet of paper looks smooth from across a room. Under magnification, its fibers become visible. A metal table feels solid, but most of the volume inside its atoms is not occupied by solid material in the everyday sense. Smoothness and solidity can be large-scale appearances produced by smaller structures. Some quantum gravity approaches suggest that areas and volumes may come in tiny units. Others suggest that space-time emerges from quantum connections or patterns of entanglement. String theory allows gravity to arise naturally from the behavior of tiny extended objects. Different ideas disagree about what lies beneath geometry, but many share the suspicion that Einstein's smooth space-time is not the deepest layer. Before reaching those proposals, it is important to appreciate how unusual Einstein's achievement was. He replaced a force with geometry. He showed that gravity changes clocks, bends light, carries waves, and influences the structure of the entire universe. His theory explained observations that Newton's theory could not, and predicted phenomena that were confirmed many years later. It also changed the meaning of empty space. In older physics, space could be viewed as a passive background. Objects moved through it, but the background itself did little. In general relativity, empty space can have structure and behavior. It can expand, it can carry waves, it can be curved even where no matter is locally present. The geometry is an active physical participant. The theory also removed the idea of one universal time. Every observer carries a personal measure of duration along a path through space-time. Two clocks that separate travel through different gravitational fields and later meet may record different amounts of time. Neither clock is malfunctioning. They have followed different routes through the geometry. This makes space-time far more flexible than the stage imagined in classical mechanics, but it remains smooth and definite. At every location, the geometry has a particular form. Curvature may change from place to place, yet it is not normally described as a cloud of several possible curvatures. That is precisely where quantum mechanics begins to press against it. If matter is quantum, then a mass can in principle occupy a combination of possible locations. General relativity says the mass determines the geometry around it. Should space-time then curve in several possible ways at once? Does each possible location produce its own possible geometry? Can those geometries interfere with one another, as quantum states do? What would it mean to measure the result? These questions cannot be answered by general relativity alone because the theory assumes classical matter and a definite space-time geometry. It does not tell us how geometry behaves when the source of gravity has no definite classical state. Trying to treat the geometry with ordinary quantum methods leads back to the mathematical problems we have already met. There is another issue hiding in the idea of location. Quantum theory normally describes a particle as being somewhere in space. General relativity tells us that space is not fixed independently of matter. If both the particle and the geometry are quantum, the phrase somewhere in space becomes harder to define. The background used to state the question is part of the uncertainty. The same applies to distance. We can ask how far apart two particles are because we assume a geometry that defines length. If the geometry fluctuates, distance may itself be a quantum quantity. Two objects could have a range of possible separations. At sufficiently small scales, there may be no single answer to how far apart they are until a physical relationship is measured. Time creates an even sharper version of this problem. Quantum theory describes change over time. General relativity makes time dependent on geometry. If the geometry is quantum, then the passage of time may also be uncertain. The ordinary structure of quantum mechanics assumes something that quantum gravity may need to explain. Einstein's theory therefore gives us both the modern understanding of gravity and the reason gravity resists a straightforward quantum treatment. Gravity is not simply another field placed inside spacetime, it is tied to spacetime itself. Quantizing gravity may require quantizing the arena in which all other quantum processes occur. That is why the phrase gentle curving can be slightly deceptive. In everyday life, spacetime curvature is gentle. The floor supports us, planets follow stable paths, and clocks remain close enough in rate that no one needs a relativity expert to arrange breakfast. In black holes and the earliest universe, the curvature becomes extreme. At the smallest scales, quantum fluctuations may make geometry restless and poorly defined. The next part of the problem lies on the other side of the disagreement. General relativity begins with a smooth spacetime and explains gravity through geometry. Quantum mechanics begins with probabilities, uncertainty, and states that can combine in ways ordinary objects never seem to do. To see why combining them is so difficult, we now need to enter that smaller world and understand why nature behaves so differently there. The smaller world does not behave like a reduced version of the larger one. An atom is not simply a tiny solar system, and an electron is not a miniature ball moving around a nucleus along a clear path. Those pictures can help at the beginning, but they soon become misleading. At the quantum scale, nature follows rules that are precise, reliable, and repeatedly confirmed, yet very different from the habits we learn from tables, bicycles, falling cups, and other objects that usually stay where we leave them. Quantum mechanics was developed because older physics could not explain what scientists were observing. Classical ideas worked well for planets, projectiles, engines, and waves in water. They began to fail when researchers studied atoms, light, and the radiation emitted by hot objects. Experiments produced patterns that did not fit the expectation that energy could vary in any amount and that particles always possess definite properties. The word quantum refers to a smallest packet or unit in certain physical processes. Energy is not always exchanged in a perfectly continuous way. In many situations, matter absorbs or releases it in distinct amounts. This discovery was not introduced because physicists wanted the universe to sound mysterious. It was introduced because the measurements refused to cooperate with older assumptions. One early problem concerned the light emitted by hot objects. Classical physics predicted that such an object should release an unlimited amount of energy at very short wavelengths. Real objects did nothing of the sort. The prediction was so badly wrong that a new idea became necessary. Max Planck proposed that energy was exchanged in separate packets. At first, this was partly a mathematical solution to a specific problem, but it became the beginning of a much larger change. Albert Einstein later used the same basic idea to explain how light can knock electrons out of a material. If light were only a smooth wave, increasing its brightness should always provide enough energy to release electrons. Experiments showed that the frequency of the light mattered more directly. Below a certain frequency, no electrons were released, no matter how bright the light became. Above that frequency, electrons could be released even when the light was faint. Einstein explained this by treating light as arriving in individual packets. Each packet carried an amount of energy related to the light's frequency. A low energy packet could not release an electron, however many similar packets arrived. It was rather like trying to open a heavy door by throwing an unlimited number of feathers at it. The effort may be admirable, but the door remains unimpressed. Light had long been known to behave as a wave. It could spread, interfere, and bend around obstacles. Now it also appeared to behave as a stream of particles. This was not a choice between two competing descriptions in which one had to be removed. Experiments showed that both aspects were necessary. Light could behave like a wave in one arrangement and produce particle-like events in another. Matter soon proved equally uncooperative. Electrons and other particles could also produce wave-like patterns. A beam of electrons directed through a suitable experimental arrangement could create interference, the kind of pattern normally associated with overlapping waves. Yet when the electrons were detected, they arrived as individual events at particular locations. The famous double-slit experiment shows this clearly. Imagine a barrier with two narrow openings and a screen behind it. If ordinary small objects are fired toward the barrier, each one passes through one opening or the other, and two main groups appear on the screen. If a wave passes through both openings, the two emerging waves overlap. In some places they strengthen each other, and in others they cancel. This produces a series of bands. When quantum particles such as electrons are sent through the openings, the final pattern resembles wave interference. That is already surprising. More surprising still, the electrons can be sent one at a time. Each arrives at the screen as a single point, but after many arrivals the points build up into the interference pattern. The behavior of each electron is connected to possibilities involving both openings, even though the final detection occurs at one place. Trying to determine which opening the electron uses changes the result. If the experiment is arranged to record a definite path, the interference pattern disappears. This does not mean that human attention has magical powers. The physical interaction required to obtain path information changes the quantum situation. Measurement is not a passive glance from a safe distance. It is an event in which the system becomes connected to an apparatus and its surroundings. Quantum mechanics describes these possibilities using a quantum state. The state contains the information needed to calculate the probabilities of different measurement outcomes. It does not normally assign one definite classical condition to every property before the measurement. An electron may not have a single precise position waiting to be discovered. Instead, its state provides a range of possible locations and the likelihood of finding it in each one. This can feel unsatisfactory, because everyday objects seem to possess definite properties whether anyone checks them or not. A chair does not appear to wait in several corners of a room until someone enters. The difference comes from scale and interaction. Large objects contain enormous numbers of particles and are constantly interacting with air, light, heat, and their surroundings. These interactions rapidly suppress the delicate quantum relationships that would allow visibly different possibilities to interfere. The process is called decoherence. It helps explain why quantum behavior becomes difficult to observe in large systems. A small, carefully isolated object can maintain a combination of possibilities. A warm, complicated object in an ordinary room becomes entangled with its environment almost immediately. Information about its state spreads into the surroundings. The separate possibilities no longer produce observable interference in the way they can for an isolated particle. Decoherence explains much of the transition from quantum possibilities to classical appearances, though it does not settle every question about measurement. It tells us why large-scale alternatives stop interfering. It does not by itself explain why a particular observer experiences one result rather than another. That issue has led to several interpretations of quantum mechanics. One traditional approach says that the quantum state provides probabilities and that measurement produces one outcome. Another view suggests that all possible outcomes continue in separate branches of reality. Other interpretations treat the quantum state as information, a tool for predicting experiences, or a description of relationships between physical systems rather than an absolute object. These interpretations often agree on the results of ordinary experiments, which makes choosing between them difficult. Fortunately, quantum mechanics does not require everyone using it to agree about what the theory means philosophically before calculating what a detector will record. The practical rules are extremely effective. Scientists use them to predict atomic spectra, chemical bonds, particle collisions, semiconductor behavior, and countless other phenomena. The disagreement concerns the deeper picture behind those predictions. Another central feature is uncertainty. In quantum mechanics, certain pairs of properties cannot both possess perfectly definite values in the same state. Position and motion provide the best-known example. A state with a very sharply defined position must have a wide range of possible motions. a state with a sharply defined motion must be spread across a wider range of positions. This uncertainty is not merely caused by poor instruments. Better equipment cannot remove it. It is part of the structure of quantum states. The more tightly one property is specified, the less tightly the related property can be specified. Nature does not always provide the full set of classical details we would like to assign. The word uncertainty can make the theory sound vague, but quantum predictions are not vague. The probabilities can be calculated with extraordinary precision. For a single event, the theory may offer several possible outcomes. For a large collection of repeated experiments, it predicts the statistical pattern very accurately. Quantum mechanics is uncertain about individual results, while being extremely reliable about distributions. Atoms demonstrate why this matters. In a classical picture, an electron moving around a nucleus should radiate energy, lose speed, and spiral inward. Stable matter would be impossible. Quantum mechanics gives the electron allowed states that do not behave like ordinary orbits. The electron is described by a spread of possibilities around the nucleus, and only certain energy levels are permitted. When an electron changes from one allowed energy level to another, the atom absorbs or releases a packet of light. Each type of atom has a distinctive set of possible transitions. This produces characteristic lines in the light it emits or absorbs. Astronomers can examine those lines in starlight and identify the elements present in stars many light years away. Quantum rules inside atoms therefore allow us to study the chemical content of distant suns without collecting a sample, which would make the journey home rather inconvenient. The same rules explain chemical bonding. Electrons in atoms can form shared quantum states. The arrangement of those states determines how atoms connect, what structures molecules form, and how substances react. The solidity of materials, the color of objects, the shape of proteins, and the operation of cells all depend on quantum behavior. This does not mean everyday biology requires a conscious calculation of quantum mechanics. A plant grows without consulting a physics textbook. The point is that the stability and interactions of the matter inside living systems follow quantum rules. Classical behavior emerges at larger scales, but it rests on a quantum foundation. Particles also possess properties that have no simple classical equivalent. One of these is called spin. The name can suggest a tiny object rotating like a ball, but that image is not quite correct. Spin is an intrinsic quantum property. It influences how particles respond to magnetic fields and how collections of identical particles can be arranged. Electrons belong to a class of particles that cannot all occupy the same quantum state. This restriction is responsible for much of the structure of matter. It determines how electrons fill the available states in atoms and helps create the organization seen in the periodic table. It also contributes to the stability of solid objects. The chair beneath you does not collapse into a tiny dense lump, partly because electrons resist being placed into identical states. Electromagnetic repulsion also plays an important role. Together, these quantum effects create the familiar resistance of matter. When you press your hand against a table, the atoms in your hand do not simply pass through the atoms in the wood. The resistance is the large-scale result of interactions governed by quantum physics. Another unusual feature is tunneling. A quantum particle can sometimes appear on the far side of a barrier, even when classical reasoning says it lacks enough energy to cross. The particle is not drilling a secret tunnel or briefly borrowing energy in the everyday sense. Its quantum state extends into and sometimes through the barrier, leaving a probability of detection on the other side. Tunneling is not a rare theoretical curiosity. It occurs in radioactive decay, electronic devices, and processes inside stars. The sun produces energy through nuclear reactions that rely partly on quantum tunneling. Positively charged atomic nuclei repel one another, and the temperature in the sun is not high enough for classical particles to overcome that repulsion often enough. Quantum tunneling allows some nuclei to get close enough to combine. Sunlight, warm afternoons, growing plants, and nearly every source of energy in Earth's food systems therefore depend on particles doing something classical physics would reject. This is a useful reminder that the quantum world is not hidden because it is unimportant. It is hidden because its strange behaviour combines into familiar effects by the time it reaches our scale. Perhaps the most discussed quantum phenomenon is entanglement. Two or more particles can share a joint quantum state in which their properties cannot be described independently. Measuring one particle produces correlations with measurements of the other, even when the particles are far apart. These correlations are stronger than any explanation based on each particle carrying a complete set of prearranged local instructions. Experiments have repeatedly confirmed this. Nature does not behave as though the particles simply agreed on their answers before separating and then revealed those answers when measured. Entanglement does not allow messages to be sent instantly across space. The result obtained at either location is still individually unpredictable. Only when the results are later compared does the pattern of correlation become visible. Relativity's limit on faster-than-light communication remains intact, though the quantum connection challenges ordinary ideas about separateness. Einstein disliked this feature and hoped a deeper theory might restore a more familiar form of reality. Later experiments showed that a broad class of local hidden explanations cannot reproduce the observed results. Quantum mechanics was not merely a temporary description hiding an ordinary mechanical system underneath, at least not one that preserves all the classical assumptions Einstein preferred. Entanglement is now treated as a practical resource. Researchers use it in quantum information, secure communication methods, precision measurement, and the development of quantum computers. What once appeared mainly as a philosophical discomfort has become something engineers try to produce and control. A quantum computer does not simply perform ordinary calculations more quickly. It uses quantum states that can represent combinations of possibilities and become entangled with one another. Certain problems can then be approached through patterns of interference that have no classical equivalent. Building such machines is difficult because the same environmental interactions that make the ordinary world look classical can destroy the required quantum coherence. Quantum field theory extends quantum mechanics and special relativity into a framework for particles and forces. In this description, fields are fundamental. A field exists throughout space, and what we call a particle is an excitation of the corresponding field. An electron is an excitation of the electron field. A particle of light is an excitation of the electromagnetic field. The vacuum is not simply empty nothingness. Even the lowest energy state of a quantum field contains fluctuations. These are not ordinary particles constantly appearing as tiny objects in a literal empty room, despite how the idea is sometimes described. They are variations built into the quantum state of the fields. Their effects can be measured in carefully arranged experiments. Particles can be created and destroyed because they are excitations rather than permanent little beads. Energy can move between fields. A collision between particles can produce different particles, provided the relevant conservation rules are satisfied. This framework has allowed physicists to describe the electromagnetic force and the forces acting inside atomic nuclei with exceptional accuracy. The collection of quantum field theories used for known non-gravitational particles and forces is called the Standard Model. It includes the basic matter particles and the particles associated with electromagnetic, strong nuclear, and weak nuclear interactions. Its predictions have been tested in particle accelerators and other experiments. Some agree with measurements to a precision that is difficult to express without a very long string of decimal places, which we shall politely leave outside tonight's discussion. Gravity is absent from this otherwise successful structure. Physicists can introduce a hypothetical quantum particle associated with gravitational interactions. It is usually called the graviton. In a simple approximation, the graviton would be a massless particle carrying gravity, just as particles of light carry the electromagnetic interaction. At low energies, this idea can be useful. Small disturbances in spacetime can be treated as quantum excitations. Gravitational waves would then correspond, in a quantum description, to large collections of gravitons, much as an ordinary light wave can be understood as involving many particles of light. The difficulty returns at very high energies. The usual methods of quantum field theory do not turn gravity into a complete predictive theory. Calculations generate an uncontrolled series of infinities. Adding a limited number of measured corrections does not solve the problem. New corrections keep appearing, each requiring more information. This failure is linked to the nature of gravity. Other quantum fields operate within spacetime. Gravity describes the structure of spacetime. When the gravitational field fluctuates, the distances and time intervals used to define all the other fields also fluctuate. The background is no longer fixed while the actors move across it. The arrangement of the theatre, the length of the performance, and the location of every seat have joined the cast. Quantum fluctuations also become stronger when shorter distances are examined. To investigate a tiny region, an experiment must concentrate a large amount of energy there. Energy itself contributes to gravity. If enough energy is concentrated into a sufficiently small region, it may form a black hole. The attempt to examine spacetime more closely could therefore hide the region behind an event horizon. This suggests a fundamental limit to ordinary measurement. At some scale, adding more energy does not reveal finer detail. It changes the geometry so dramatically that the detail becomes inaccessible. The combination of quantum uncertainty and gravitational collapse may prevent space from being divided into endlessly smaller operational regions. Physicists often associate this limit with an extremely tiny scale, where quantum effects and gravity should become equally important. At that scale, the familiar idea of smooth spacetime may fail. Distances could fluctuate strongly. Short-lived geometric structures might appear. The distinction between one location and another could lose its usual meaning. Some descriptions use the phrase space-time foam, suggesting a restless microscopic geometry. The phrase is useful as a rough image, but no one should imagine literal bubbles made from the same material as bath foam. It refers to the possibility that geometry at tiny scales is highly variable, and unlike the smooth space-time described by general relativity. The quantum world therefore creates a direct challenge for gravity. Every physical field we have successfully examined shows quantum behavior. Matter can occupy combinations of states. Fields fluctuate, particles become entangled, measurements produce probabilistic outcomes. It would be surprising if gravity alone remained completely classical, while everything producing gravity was quantum. Suppose a small mass is prepared in a combination of two locations. General relativity says mass curves spacetime. Does the mass create one gravitational field, two possible fields, or a quantum combination of geometries? If another object responds to that gravity, can the gravitational interaction entangle the two objects? These questions are becoming targets for laboratory experiments. A successful experiment showing that gravity can generate entanglement would provide strong evidence that gravity carries quantum information. It would not reveal the complete theory of quantum gravity, but it would make a purely classical description much harder to maintain. Researchers are working towards such tests using tiny masses placed in carefully controlled quantum states. The technical obstacles are considerable. Gravity between small objects is extremely weak. Electromagnetic forces, vibration, heat, and environmental noise can overwhelm it. The masses must be isolated while their quantum coherence is preserved. Even the slightest unwanted interaction can produce an effect larger than the gravitational signal. Yet these experiments are important because they bring quantum gravity closer to the laboratory. For many years, the subject was associated mainly with unreachable energies, black hole interiors, and the beginning of the universe. Tabletop tests may not reproduce those extreme environments, but they can examine basic questions about whether gravity participates in quantum entanglement. The deeper issue remains unresolved. Quantum mechanics assumes that systems evolve according to quantum rules, often against a defined background of space and time. General relativity says that the background is a physical system influenced by matter and energy. Combining them requires a description in which geometry can be uncertain, entangled, and subject to quantum change. That description must also explain why ordinary spacetime appears smooth. We do not see distances jumping between values. We do not notice tables occupying visibly different geometries. Clocks behave consistently, apart from the small relativistic effects already measured. Whatever occurs at the deepest level must produce the stable, large-scale world described by Einstein. This is similar to the way quantum behavior produces classical matter. A single electron follows unfamiliar rules, but a collection of enormous numbers of particles can form a solid object with a clear location. A deeper theory may show how a quantum structure produces a continuous spacetime. General relativity would then be the large-scale approximation, accurate in the same way that fluid mechanics accurately describes water without tracking every molecule. The comparison has limits. Molecules exist in space, while the hypothetical ingredients of spacetime cannot simply be placed inside a more basic ordinary space without moving the problem elsewhere. If spacetime emerges, it must emerge from relationships that do not already assume the geometry they are meant to explain. Entanglement may offer part of the answer. Some modern approaches suggest that spatial connections are related to patterns of quantum entanglement. Regions that are strongly entangled may appear close together in an emergent geometry. Changes in those relationships could correspond to changes in curvature. In this view, space is built from quantum connections rather than serving as the container for them. Other approaches begin with discrete units of geometry. Areas and volumes may have smallest possible values, produced by networks of quantum states. Smooth space would appear only when many units are viewed together. Still other theories replace point particles with tiny extended objects, whose quantum behavior naturally includes a gravitational mode. Each proposal is responding to the same central difficulty. Quantum physics says that the small-scale world cannot be described using definite classical properties. General relativity says gravity is the geometry of space and time. A quantum theory of gravity must therefore allow geometry itself to enter the uncertain and entangled world. Once that step is taken, familiar questions become difficult to state. Where is an event if space has no definite geometry? How long does a process take if time is part of a quantum state? What counts as a cause when the order of events can depend on fluctuating space-time? How can probabilities be defined for the entire universe when there is no external observer or clock? These questions are not signs that quantum mechanics has failed. They show that the usual form of quantum mechanics may depend on structures that gravity makes dynamic. The theory works brilliantly when a background time and space can be assumed. At the point where the background itself must be quantized, the standard language begins to strain. The strain becomes visible in calculations, especially where extremely short distances and high energies are involved. The quantities that should describe interactions grow without control. Predictions require more and more arbitrary corrections. Instead of producing a clear answer, the mathematical procedure demands an endless supply of new information. That is the point where the disagreement stops being a contrast between two unusual views of nature and becomes a breakdown in the machinery of prediction. General relativity tells us how space-time responds to matter. Quantum theory tells us how matter behaves at the smallest scales. When both must operate without approximation, the usual equations no longer provide a complete answer, and the exact places where they fail reveal what the missing theory must repair. The strain becomes visible when physicists try to use the ordinary rules of quantum field theory to describe gravity at extremely short distances. At low energies, the procedure works reasonably well. Gravity can be treated as a weak interaction, and small quantum corrections can be calculated. The answers are useful, consistent, and do not cause immediate alarm. This is why physicists can discuss particles associated with gravitational waves or estimate tiny quantum effects without already possessing a complete theory of quantum gravity. The trouble grows as the energy increases. Higher energy allows researchers to examine smaller distances. This is a general feature of particle physics. If you want to see the structure of something tiny, you need a probe with a very short wavelength, and producing that probe requires more energy. A gentle beam may reveal the outline of an object. A more energetic beam can reveal finer details. Continue far enough, however, and gravity begins to respond to the energy used in the investigation. Energy is not separate from gravity. In general relativity, energy contributes to the curvature of spacetime. Concentrating more energy into a smaller region therefore strengthens the gravitational effect in that region. The tool used to inspect the smallest scales begins changing the thing being inspected. Add enough energy, and the region may become hidden behind an event horizon. This creates an unusual limit. In many areas of science, increasing the power of an instrument improves the measurement. In quantum gravity, increasing the energy may eventually make the target less accessible. The microscope does not merely disturb the sample, it threatens to turn the sample into a black hole. Long before that dramatic point is reached, the calculations already begin to misbehave. Quantum field theory describes interactions by considering all the possible ways particles and fields can influence one another. A simple process may be represented by a basic interaction. More accurate calculations include additional possibilities, such as temporary disturbances in the fields and repeated interactions between particles. Each added layer provides a smaller correction to the earlier answer. For the electromagnetic and nuclear forces, this procedure can be controlled. The raw calculations sometimes produce infinite quantities, but physicists have a method for dealing with them. The infinities can be collected into a limited number of physical properties, such as measured masses and interaction strengths. Once those properties are fixed by experiments, the theory produces finite predictions. This method is called renormalization. The word may sound as though someone adjusted the settings until the mathematics stopped complaining. There is more discipline involved than that. Renormalization is a precise framework for separating quantities that depend on the chosen description from quantities that can be measured. It has been tested through some of the most accurate predictions in all of science. The electromagnetic theory of electrons and light is a famous example. Its predictions agree with experiments to an astonishing degree. The theory contains mathematical infinities during intermediate steps, yet the final measurable answers are finite and reliable. The infinities do not mean the theory is useless. They mean the quantities must be organized in the correct way. Gravity refuses to cooperate so neatly. When general relativity is treated as an ordinary quantum field theory, new infinities appear at every increasing level of precision. Each one seems to require a new correction. Then further calculations require more corrections, followed by still more after that. Instead of measuring a small set of properties and using them to predict everything else, physicists would need an endless list of measurements. A theory that requires infinitely many independent pieces of experimental information cannot make useful fundamental predictions. It can describe known behavior only after being supplied with an unlimited number of instructions. That is rather like claiming to predict tomorrow's weather after being told the temperature and rainfall at every location for every minute of tomorrow. The answer may be correct, but the predictive achievement has quietly left the room. This failure does not appear because physicists have made a small technical mistake. It reflects a deeper difference between gravity and the other interactions. The electromagnetic field exists in space-time. The fields associated with nuclear forces also exist in space-time. Their particles move through a background geometry that can usually be treated as fixed. Gravity is different because the gravitational field is the geometry. When gravity fluctuates, the background used to define positions, distances, energies, and durations fluctuates with it. The usual mathematical methods assume that events occur at locations that can be identified. A particle interacts with another particle at a point in space-time. The distance between points can be calculated. Time passes according to a known background structure. When space-time itself becomes quantum, these assumptions no longer remain safely in place. A location may not be definite, A distance may have several possible values. The duration between two events may fluctuate. Even the order of events may become difficult to define in the ordinary way. The theory is being asked to calculate quantum behavior using a stage whose shape, size, and timing are part of the quantum behavior. This is why simply treating gravity like one more force is not enough. The method can provide a useful approximation when spacetime is almost flat and quantum gravitational effects are small. It fails when the geometry itself becomes strongly quantum. The same warning appears in general relativity from another direction. The theory predicts singularities. A singularity is not simply an object with a dramatic name. It is a place where the quantities used by the theory grow without limit, or where the description can no longer be extended. At the center of a classical black hole, space-time curvature becomes unlimited. When the expansion of the universe is followed backward, the equations approach another singular state. These results do not necessarily prove that infinite density or infinite curvature physically exists. They may instead show that general relativity has been pushed beyond its range. A similar thing happens when a map ends at the edge of the paper. The blank space does not prove the landscape disappears. It proves the map is incomplete. The black hole singularity is particularly important because nothing in classical general relativity stops matter from collapsing toward it after crossing the event horizon. The geometry directs every future path inward. As matter becomes more compressed, curvature grows stronger. Eventually, the theory reaches a point where it cannot say what happens next. Quantum mechanics should matter in such a small region, but ordinary quantum mechanics expects a background time and space. Near the singularity, that background is precisely what has lost its ordinary meaning. We cannot simply place quantum matter inside the classical geometry and continue. The geometry itself must join the quantum description. The beginning of the universe produces the same demand. General relativity describes expansion very successfully after the universe reaches conditions where the geometry can be treated classically. Move closer to the earlier stage, and matter becomes denser, temperatures increase, and the relevant distances shrink. Quantum effects become unavoidable. The theory then asks for an initial condition at a point where its own concepts no longer work. What does before mean if time is part of the geometry that is breaking down? What does size mean if distance is no longer classically defined? What does density mean if the volume being used in the calculation is subject to quantum uncertainty? These are not word games. They reveal that familiar concepts depend on the physical structure they are supposed to describe. Density requires an amount of matter and a volume. Duration requires a clock and a definition of time. Location requires a geometry. If the geometry is quantum, these quantities may not possess the fixed values assumed by classical physics. Black hole evaporation adds another failure, this time involving information. A black hole forms from matter in a particular physical state. That matter may contain an enormous amount of detailed information. It has particles arranged in certain ways, carrying particular energies, motions, and quantum relationships. Once the matter crosses the event horizon, an outside observer can no longer examine those details directly. Classical general relativity says the final black hole can be described using only a few overall properties. Much of the detailed information appears to be hidden. This alone does not violate quantum theory because information can be inaccessible without being destroyed. A locked room may contain a detailed library even if someone outside can read only the label on the door. The serious problem begins when quantum effects cause the black hole to radiate. The radiation predicted by Stephen Hawking appears thermal. Its basic properties depend on the black hole, rather than on the detailed nature of everything that fell inside. As the black hole radiates, it loses mass. Given enough time, it may disappear completely. If the outgoing radiation contains no detailed record of the infalling matter, and if the black hole eventually vanishes, the information seems to be gone. Quantum mechanics does not normally allow this. A quantum state may become complicated beyond practical recovery. but its information should remain encoded in the later state. The problem is not solved by saying that the information remains at the singularity. If the black hole disappears, the singularity should disappear with it. Leaving the information in a final tiny remnant creates other difficulties. Such a remnant might need to store an unlimited number of possible states inside an extremely small object. Producing and controlling such objects would create problems of its own. Many physicists now believe the information escapes through subtle correlations in the radiation. The radiation may look thermal when examined approximately while still carrying the complete information in a highly scrambled form. This idea protects quantum mechanics, but it raises a difficult question. How does information move from the interior to the outgoing radiation if the event horizon prevents ordinary signals from escaping? Solving this problem seems to require a major change in how spacetime, horizons, and quantum information are related. Some proposals suggest that information is stored at the boundary of the black hole. Others suggest that the interior is encoded in quantum relationships involving the outside. Some challenge the idea that the horizon is smooth. Others suggest that space itself emerges from patterns of entanglement. The black hole has therefore become more than an unusual astronomical object. It is a laboratory for testing the consistency of fundamental ideas. General relativity describes the geometry of the horizon and interior. Quantum theory demands the preservation of information. Thermodynamics assigns the black hole a temperature and an entropy. A complete theory must make all three descriptions agree. Entropy creates another clue. A black hole has an amount of entropy related to the area of its horizon, not the volume inside it. This is surprising because ordinary physical systems usually store information throughout their volume. A box of gas has more possible microscopic arrangements when the box is larger. One might expect a black hole to behave similarly. Instead, the information capacity appears tied to the surface area. This suggests that a region of space may be describable using information stored on its boundary. The idea is known as the holographic principle. It does not mean the universe is a visual projection in the everyday sense. It means that the complete physics inside a region may have an equivalent description on a lower dimensional boundary. This possibility emerged because the usual equations produced contradictions. The breakdown forced physicists to reconsider where information is stored and whether the interior of space is fundamental. The mathematics also struggles when physicists try to define the quantum state of the entire universe. In ordinary quantum mechanics, a system is observed from outside. A laboratory apparatus records a result. A clock measures the evolution. The environment helps turn delicate quantum possibilities into stable classical outcomes. The universe has no external laboratory. There is no clock outside it, no surrounding environment, and no observer standing beyond space and time. A theory of quantum cosmology must describe everything within one system, including the clocks, measuring devices, observers, and geometry. This produces the problem of time in its strongest form. Some attempts to quantize the whole universe lead to a description in which the usual time variable disappears. The fundamental equation does not show the universe evolving from one moment to another. It describes a complete quantum state without an external clock. The result can look as though the universe is frozen. Nothing changes because there is no background time in which change can occur. Yet the world we experience is full of change. Stars form and die. Particles decay. People forget why they walked into a room and then remember immediately after leaving it. The challenge is to explain how ordinary time emerges from a timeless, fundamental description. One physical system may serve as a clock relative to another. Change may be defined through correlations. The universe does not evolve with respect to an outside time. Its parts change relative to one another. This relational approach may work, but turning it into a complete theory is difficult. Different choices of clock can lead to different descriptions. A clock is a physical object and therefore subject to quantum uncertainty. No clock is perfectly accurate. In extreme conditions, the distinction between the clock and the system being measured can become unclear. The ordinary meaning of probability also becomes complicated. In laboratory quantum mechanics, an experiment can be repeated many times. The probabilities predict how often each result will occur. There is only one observable universe, and its entire history cannot be restarted under identical conditions. Physicists can still use probabilities in cosmology, but interpreting them requires care. Are they probabilities for different possible universes? Are they predictions for observations made within one universe? What determines which observations are typical? These questions become important when a theory allows many possible cosmic histories. Another breakdown appears when spacetime geometry fluctuates strongly. General relativity depends on the idea that nearby points and smooth paths can be defined. Quantum theory allows fluctuations at every scale. If those fluctuations become large enough, the concept of a smooth path may fail. A particle normally moves from one event to another through spacetime. Near the scale where quantum gravity dominates, it may be impossible to define one background geometry for the journey. Several possible geometries may contribute. The particle is not merely uncertain about which path it takes. The available paths and the distances between them are themselves uncertain. Ordinary ideas of locality then become difficult. Locality means that physical interactions occur at nearby points, and that influences do not jump arbitrarily across space. It is central to quantum field theory and relativity. If space is not fundamental, closeness may be an emergent relationship rather than a basic fact. Two elements that appear distant in the large-scale geometry might be directly connected in the deeper quantum structure. Two elements that appear close might have only an indirect connection. A successful theory must explain why ordinary locality emerges so reliably at familiar scales. Causality faces a similar challenge. Relativity organizes events using the structure of light signals. One event can influence another only if the geometry allows a signal to travel between them. If the geometry fluctuates, the causal relationship may also fluctuate. In one possible geometry, one event may occur before another. In a different geometry, the order may be reversed or undefined. Quantum theory can allow combinations of possibilities. This raises the prospect of quantum states in which causal order itself is not definite. Experiments in quantum information have explored processes without one fixed classical order, although these do not yet provide a complete model of quantum spacetime. They show that causal structure may be less rigid than ordinary experience suggests. Quantum gravity may need to explain why a definite sequence of causes and effects emerges in the world around us. The measurement problem also becomes sharper when gravity is involved. Quantum theory allows a system to exist in a combination of possible states. General relativity says each distribution of matter creates a corresponding geometry. If a mass occupies two possible locations, the gravitational field should somehow reflect both possibilities. A measuring device can detect where the mass is, but the device is made of matter and also produces gravity. The system, the detector, and spacetime are all connected. There is no simple classical background separating the observer from the observed. Some physicists have wondered whether gravity itself causes quantum possibilities to collapse into one result. In this view, very different mass distributions would correspond to incompatible spacetime geometries, and the combination could not survive indefinitely. The gravitational difference might force a definite outcome. This idea is interesting because it connects the measurement problem with quantum gravity, but it remains unconfirmed. Experiments are testing whether increasingly massive objects can maintain quantum combinations for long periods. So far, quantum theory continues to work as larger systems are isolated, though the technical challenge grows rapidly. Other researchers expect gravity to remain fully quantum and believe ordinary decoherence explains why large objects appear definite. The geometry becomes entangled with matter and the environment, making interference impossible to observe. No special gravitational collapse would be needed. The disagreement illustrates how little is known at the meeting point. The existing theories give several possible directions but no decisive answer. There is a further practical difficulty. The scale where quantum gravity effects are expected to become strong is extremely remote from current experiments. Particle accelerators cannot reach it directly. Creating the required energy would demand machinery far beyond anything humans can build. This does not make the theory untestable, but it changes the search. Physicists look for amplified or accumulated effects. A tiny change repeated over a vast distance might become observable. Light from distant cosmic sources could carry traces of microscopic space-time structure. Gravitational waves might reveal departures from classical behavior. The early universe may have magnified quantum gravitational fluctuations into patterns spread across the sky. Every proposed signal must be treated carefully. Astrophysical environments are complicated. A strange observation may come from ordinary matter, unknown features of a source, or limitations in the instrument. Quantum gravity is not the only explanation available whenever a telescope sees something unexpected. Laboratory experiments offer a different path. Researchers are developing ways to place small masses into quantum states and measure the gravitational interaction between them. If gravity can create entanglement, it must be capable of carrying quantum information. That would rule out many purely classical descriptions. Even this would not tell us what spacetime is made of. It would establish that the missing theory must be quantum in an important sense. It would narrow the search rather than complete it. The equations fall apart in several connected ways. Quantum calculations of gravity produce uncontrolled infinities. General relativity predicts singularities where its geometry loses meaning. Black holes threaten the quantum preservation of information. Cosmology removes the external time used by ordinary quantum theory. Strong quantum fluctuations challenge location, distance, locality, and causal order. These failures are not random. They gather around the same extreme conditions: very high energy, very small distance, very strong gravity, horizons, singularities, the earliest universe. Each points toward a level at which smooth space-time and ordinary quantum fields are no longer separate ingredients. A complete theory must replace the infinities with finite predictions. It must explain what happens where singularities appear. It must preserve or consistently modify quantum information. It must show how time and space emerge, if they are not fundamental. It must recover Einstein's geometry at large scales, and the standard quantum description of matter when gravity is weak. That is an unusually demanding list, which is why the problem has survived for so long. The existing theories are not slightly inaccurate guesses waiting for a minor correction. They are deeply successful frameworks built on different foundations. Joining them may require changing the foundations themselves. Physicists have therefore explored several possible starting points. Some replace point particles with tiny extended objects, allowing gravity to appear naturally among their quantum vibrations. Some rebuild geometry from discrete loops and networks. Some treat space-time as an emergent result of quantum information. Some begin with causal relationships rather than distances. Each approach tries to remove the failures without losing the enormous success of the theories we already have. The equations have shown where the old language stops working. The next task is to find a language that can continue beyond that point, and the leading proposals begin with very different ideas about what the smallest ingredients of reality might be. The leading proposals begin with very different ideas about what the smallest ingredients of reality might be. This is not because physicists enjoy making an already difficult subject harder, although some conference schedules may suggest otherwise. It is because the failures of the current theories do not point to one obvious repair. They tell us that something must change, but they do not tell us whether the missing ingredient is a new kind of particle, a new kind of geometry, a new rule for quantum theory, or a deeper structure from which both matter and space-time emerge. Any proposed bridge between quantum mechanics and gravity must satisfy several strict conditions. It must behave like quantum theory when gravity is weak. It must reproduce general relativity when distances are large and space-time is smooth. It must explain why black holes have temperature and entropy. It should remove singularities or show why they are not physical. It must remain mathematically consistent at very high energies. Most importantly, it must eventually make predictions that can be tested. That last requirement is the most difficult. Many ideas can be made interesting on paper. Far fewer can be connected to an observation. Quantum gravity operates most strongly at distances far smaller than present experiments can reach directly. Theories are therefore judged through a mixture of mathematical consistency, agreement with known physics, and their ability to produce clues that might appear in cosmology, particle physics, gravitational waves, or black holes. The most widely known proposal is string theory. Its starting point is simple to state. The fundamental objects of nature may not be point-like particles. They may be tiny, one-dimensional strings. A point particle has no length or internal shape. It is treated as existing at one location. A string has a small but finite extension. It can vibrate in different ways. Each pattern of vibration appears, at larger scales, as a different kind of particle. The comparison with a musical string is useful, though the physical object would be far smaller than anything that could be seen. A guitar string can vibrate in several patterns and produce different notes. In string theory, different vibrations would produce particles with different masses, charges, and other properties. An electron would correspond to one pattern. Other particles would correspond to other patterns. The basic ingredient could be the same while its modes of vibration create the variety observed in nature. This change from points to strings helps with quantum gravity. Interactions between point particles are imagined as occurring at exact locations. At very high energies, those sharply localized interactions contribute to the infinities that make gravity difficult to control. A string spreads the interaction over a small length. The process becomes less abrupt, which softens the mathematical behavior at short distances. Gravity also appears naturally in the theory. When a quantum string is allowed to vibrate in every permitted way, one of its possible vibration patterns behaves like the expected quantum particle of gravity. Physicists did not need to insert this gravitational particle by hand. It emerged from the mathematics. This was one of the major reasons string theory attracted so much interest. A theory originally explored for other purposes unexpectedly contained gravity. It also offered a framework in which gravity could be treated quantum mechanically without producing the same uncontrolled infinities found in the Dirac point particle approach. The promise came with additional requirements. String theory is mathematically consistent only when space-time has more dimensions than the 3 dimensions of space and 1 dimension of time that we experience directly. The exact number depends on the version of the theory, but the extra dimensions are a central feature. These dimensions are not usually imagined as large directions in which someone could casually wander and become late for dinner. They may be curled into extremely small shapes, present at every point in familiar space but hidden from ordinary observation. The shape of these compact dimensions affects how strings can vibrate and therefore influences which particles and forces appear at larger scales. This provides both an opportunity and a problem. The extra geometry might explain why particles have their observed properties. Different shapes could lead to different physical laws. Unfortunately, there are many possible shapes, and each may produce a different version of low-energy physics. Instead of giving one obvious description of our universe, string theory appears to allow an enormous collection of possible solutions. This collection is often called the landscape. Each solution may correspond to different particles, different interaction strengths, and different large-scale behavior. Researchers try to identify principles that would select the solution matching our universe. Perhaps cosmology favors certain possibilities. perhaps mathematical consistency, removes most of them. Perhaps the universe occupies one state among many because only some states permit complex structures and observers. None of these ideas has yet produced a universally accepted answer. String theory also includes objects with more dimensions than strings. These extended objects are known as branes. A string is extended in one spatial direction. A brane can extend across 2, 3, or more directions. Some models suggest that the familiar universe could be associated with a brane inside a larger dimensional structure. In such a picture, ordinary particles and forces might be confined to the brane, while gravity can spread into the surrounding dimensions. This could help explain why gravity appears so weak compared with the other forces. Its influence may be diluted because it has more directions through which to spread. No experimental evidence has confirmed this idea, but it has inspired searches for deviations from ordinary gravity at short distances, unusual particle collider events, and signs of extra dimensions in cosmology. So far, the familiar dimensions have kept their additional neighbours well hidden. String theory is not one isolated model. Several versions were developed, and they initially looked like competing theories. Later work showed that these versions are connected through mathematical relationships called dualities. A difficult calculation in one description can sometimes become easier in another. What looks like a strong interaction in one theory may appear as a weak interaction in its dual form. These relationships suggested that the separate string theories are limits of a deeper framework, often called M-theory. The full nature of that framework remains incomplete. It appears to include strings, branes, additional dimensions, and relationships that connect different descriptions of the same physics. The word theory can make this sound more finished than it is. In physics, a theory can refer to a mathematical framework under active development. M-theory is not yet a complete set of equations that answers every question. It is more like a network of clues showing that apparently different models belong to one larger structure. String theory has produced major advances in mathematics and in the study of black holes. It has successfully counted microscopic states associated with the entropy of certain idealized black holes. It has also led to a powerful form of holographic duality, in which a gravitational theory inside a region can be equivalent to a quantum theory, without gravity on its boundary. These achievements are important even though direct evidence for strings has not been found. They show that the framework can connect gravity, quantum mechanics, thermodynamics, and information in precise ways. Whether the theory describes our universe in full remains unresolved. A very different proposal begins without replacing particles with strings. Loop quantum gravity focuses directly on the quantum nature of spacetime. General relativity says geometry is dynamic. Loop quantum gravity takes that statement seriously and applies quantum rules to geometry itself. Instead of treating space as a smooth background, the theory describes it through networks of quantum relationships. These networks are often represented as graphs made of links and meeting points. The links carry information related to areas, while the meeting points carry information related to volumes. They are not meant to be tiny wires placed inside ordinary space. They are the structure from which space may be built. In this picture, geometry comes in discrete units. Area and volume cannot take every possible value. They occur in separate allowed amounts, rather as atomic energy comes in separate levels. Smooth space appears when an enormous number of these quantum units are viewed together. The effect would be similar to a digital image. From a normal viewing distance, the picture looks continuous. Under sufficient magnification, individual pixels become visible. Loop quantum gravity does not claim that space is literally made of square pixels. The comparison only shows how a continuous appearance can emerge from discrete ingredients. Time and change are introduced through evolving networks. The links and meeting points can rearrange, creating a history sometimes described as a spin foam. Again, the name is technical rather than literal. No one expects the universe to feel soft and bubbly if examined with a sufficiently small spoon. One attraction of loop quantum gravity is that it does not require a fixed background spacetime. The geometry is part of the quantum system from the beginning. This respects a central lesson of general relativity, which says spacetime is not a passive container. The theory has also been applied to black holes and the early universe. In some models, quantum geometry replaces the classical singularity inside a black hole. Matter may reach a maximum density rather than collapsing without limit. The interior could continue into another region, undergo a transition, or produce a later release of information. These possibilities depend on the model and remain uncertain. In quantum cosmology inspired by loop methods, the beginning of the universe may be replaced by a bounce. Instead of emerging from an infinite classical singularity, an earlier contracting phase reaches a high but finite density and then begins expanding. Quantum geometry creates an effective repulsion under extreme conditions, preventing unlimited collapse. This is an appealing result because it removes the singularity, but it is not yet confirmed. Researchers study whether such a bounce would leave traces in the distribution of matter or in ancient radiation. The predictions can depend on assumptions about the early universe, making clear tests difficult. Loop quantum gravity also faces the challenge of recovering ordinary spacetime. It can describe quantum units of geometry, but showing in full detail how a smooth four-dimensional universe governed by general relativity emerges from them is a demanding task. The theory must also incorporate the known particles and forces of the standard model in a natural way. String theory begins with a framework that includes matter and gravity, but introduces extra dimensions and many possible solutions. Loop quantum gravity begins with quantum geometry and stays close to the principles of general relativity, but connecting it completely to familiar particle physics remains difficult. The two approaches are sometimes presented as opponents, though the real situation is less dramatic. They ask different questions and emphasize different requirements. Some researchers work within one program, others borrow methods across fields. A final theory could resemble one of them, combine ideas from several, or take a direction no current proposal is fully anticipated. Another approach is called causal dynamical triangulation. It attempts to build spacetime from simple geometric pieces. These pieces can be assembled in many possible ways, creating different candidate geometries. Quantum rules are used to consider the contributions of those possibilities. The word triangulation comes from the use of basic building blocks similar to triangles and their higher dimensional counterparts. A curved surface can be approximated by joining many small flat pieces. A globe, for example, can be represented by a mesh of flat faces. Use enough pieces and the larger shape becomes smooth. In causal dynamical triangulation, the pieces are arranged while preserving a distinction between space and time. This causal structure prevents the geometry from becoming completely uncontrolled. Researchers then study whether a realistic large-scale spacetime emerges from the combined quantum possibilities. An encouraging result is that a universe with familiar dimensions can appear at large scales in certain calculations, even though the construction begins with more basic pieces. At extremely short distances, the effective number of dimensions may change. Spacetime could behave as though it has fewer dimensions when examined very closely. This idea of changing dimension appears in several approaches to quantum gravity. The universe may look four-dimensional at ordinary scales, but possess a different effective structure in the smallest regime. That could improve the high-energy behavior of gravity and help control infinities. A related proposal known as causal set theory begins with events and their causal order. Instead of assuming a continuous spacetime, it treats reality as a discrete collection of elementary events. The most basic information is which events can influence which others. Distance and geometry would then emerge from this causal network. The theory begins with before and after rather than with a smooth background. If enough events are arranged in the right pattern, their relationships can approximate the space-time described by general relativity. This approach reflects an important lesson. Spacetime geometry may contain more information than is truly fundamental. Perhaps the deepest structure does not need lengths and angles. It may need only a record of possible influence. Other researchers explore asymptotic safety. This proposal does not necessarily replace general relativity with strings or discrete geometry. Instead, it asks whether gravity can remain a meaningful quantum field theory if its interaction strength approaches a special stable behavior at very high energies. The direct quantum treatment of gravity fails because more corrections appear at every stage. Asymptotic safety suggests that the theory might settle into a high-energy regime controlled by a fixed pattern. If that happens, only a limited number of physical parameters may be needed, restoring predictive power. Evidence for this possibility has appeared in several approximate calculations. The difficulty is proving that the required stable behavior exists in the complete theory and showing exactly what it predicts. If successful, asymptotic safety would be a relatively conservative bridge. General relativity would not be replaced by a completely different foundation. Its quantum behavior would become controlled in an unexpected way. There are also proposals in which gravity is not fundamental at all. It may emerge from thermodynamics, quantum information, or the collective behavior of deeper microscopic elements. Temperature provides a useful comparison. No single molecule possesses the temperature of a room in the ordinary sense. Temperature describes the average behavior of many particles. It is real and measurable, but it is not fundamental at the level of one molecule. Gravity might be similar. The curvature of space-time could be a large-scale description of many underlying quantum relationships. Einstein's equations might then resemble the laws of fluid motion. They would be extremely accurate at large scales without describing the smallest ingredients directly. Several discoveries support taking this idea seriously. Black holes connect gravity with temperature and entropy. Their horizons behave like thermodynamic systems. The amount of information they can store depends on area. These facts suggest that space-time geometry, heat, and information are deeply related. In some approaches, gravitational behavior arises from changes in entanglement. Quantum systems contain patterns of connection that determine how information is shared. Altering those patterns may change the geometry that emerges. Curved space-time could reflect the organization of quantum information. This does not yet provide one complete theory. It is a direction of research linking quantum information, field theory, gravity, and thermodynamics. It has become especially influential because it gives new tools for studying black holes and holography. Twistor theory takes another route. It reorganizes the description of space-time using mathematical objects that treat light rays and causal relationships as basic. The goal is to simplify the structure of relativity in quantum fields by replacing ordinary space-time coordinates with a different language. Twistor methods have produced powerful techniques for calculating particle interactions. Whether they can lead to a full theory of quantum gravity remains uncertain, but they show that changing the mathematical viewpoint can reveal structures hidden in the usual description. Group field theory, tensor models, and related approaches attempt to build space-time from quantum building blocks, whose collective behavior resembles geometry. These programs share features with loop quantum gravity and with methods used in many particle systems. A large number of simple quantum elements may pass through phases, just as matter can change from liquid to solid. Space-time itself might be a phase of an underlying system. Under some conditions, the basic elements form a smooth geometry. Under others, there may be no recognizable space. The beginning of the universe could then be interpreted not as the start of everything, but as a transition into a geometric phase. This possibility changes the question of what came before. If time and space emerge only after the transition, before may not be an ordinary temporal direction. Asking what happened earlier could be like asking what lies north of the northernmost point. The question uses a concept beyond the region where that concept applies. The challenge for every emergent model is to explain ordinary experience. A proposal must show why three large spatial dimensions appear: why time behaves differently from space, why locality works, and why general relativity describes the resulting geometry. It must also explain how known particles and forces fit into the same structure. There are attempts to modify quantum mechanics rather than gravity. Perhaps the standard quantum rules fail for sufficiently massive objects or strong gravitational fields. A gravity-related collapse process might force quantum possibilities to become definite. This could solve part of the measurement problem while preventing the most troublesome combinations of spacetime geometries. Experiments are testing whether quantum combinations survive in larger and heavier systems. So far, no confirmed departure from standard quantum theory has appeared. Improved experiments may either reveal a gravitational modification or push such models into narrower ranges. Other proposals modify the behavior of spacetime at short distances. The fundamental relationships between position and motion may change. There may be a smallest measurable length. Particles may experience tiny violations of familiar symmetries. Light of different energies might travel slightly differently across enormous cosmic distances. Astronomers search for these effects using distant explosions and high-energy particles. The results have placed strict limits on many models. No clear quantum gravity signal has been found, but negative results are useful. They tell theorists which forms of microscopic structure are unlikely. The variety of proposals can make the field seem scattered. In reality, several common themes appear again and again. Smooth spacetime may not remain smooth at the smallest scale. Locality may emerge rather than exist fundamentally. Information may be more basic than geometry. Time may arise from relationships between quantum systems. Black hole entropy may reveal the number of microscopic states of spacetime. A successful theory may need to explain matter and geometry together, rather than treating one as the occupant and the other as the container. The approaches also exchange ideas. Holography grew largely from string theory, but now influences many areas. Discrete geometry appears in loop methods, causal sets, and triangulated models. Renormalization techniques are used in asymptotic safety and group field theory. Quantum information has become a common language for researchers who began in very different traditions. No candidate has yet satisfied every requirement and received clear experimental support. String theory has achieved deep mathematical unity and strong results for certain black holes, but it has not produced a unique confirmed model of our universe. Loop quantum gravity gives a direct quantum description of geometry, but its connection to ordinary particles and complete large-scale physics remains under development. Other approaches offer promising pieces without yet forming a finished structure. This may be expected. General relativity required new ideas about geometry. Quantum mechanics required new ideas about probability, measurement, and physical properties. Their unification may demand a conceptual step that is difficult to recognize from within either theory. The final answer may not select one current proposal exactly as it stands. Research programs often act as collections of tools and partial insights. One may correctly describe quantum geometry. Another may reveal how information is stored. A third may provide the right high-energy behavior. The complete theory could combine these lessons in a way that makes their present disagreements look less important. Nature will decide through evidence, but finding the right evidence requires knowing where to look. The most useful clues may not come from trying to observe strings or loops directly. They may come from places where gravity, quantum mechanics, and information are already forced together. Black holes provide exactly that environment. They curve space-time strongly, produce quantum radiation, carry entropy, hide information behind horizons, and lead classical equations toward singularities. They are not merely objects that a theory of quantum gravity should explain. They may be the objects already showing us how the bridge is built, especially when their interiors, boundaries, and stored information are examined together. Black holes bring all the major problems together in one place. They are predicted by general relativity, affected by quantum mechanics, described by thermodynamics, and deeply connected to information. Each theory tells us something important about them, but the descriptions do not fit together without creating difficult questions. That is why black holes have become one of the main testing grounds for quantum gravity. For a long time, black holes were treated as objects that could only absorb. Matter could fall into them, light could fall into them, nothing could return once it crossed the event horizon. From the outside, the black hole would grow as it gained mass, but it would not release anything of its own. That picture began to change when physicists studied black holes using ideas from thermodynamics. Thermodynamics describes heat, temperature, energy, and entropy. It was developed to explain engines, gases, and the movement of heat, but its principles apply much more widely. Entropy is especially important. It measures the number of microscopic arrangements that can produce the same large-scale condition. Consider a cup of warm tea. At the large scale, we can describe its temperature, volume, and pressure. At the microscopic scale, an enormous number of molecules are moving in different directions with different speeds. Many different detailed arrangements can produce the same measured temperature. Entropy reflects the number of those possible arrangements. A highly ordered system has fewer possible microscopic arrangements. A disordered system has more. This is why entropy tends to increase. There are far more ways for energy to be spread out than there are for it to remain concentrated in one tidy location. Black holes seemed, at first, to have nothing to do with this. They were objects defined by gravity. Then physicist Jacob Bekenstein noticed a serious problem. Suppose a box of hot matter falls into a black hole. The matter has entropy. Once it crosses the horizon, its details disappear from the outside universe. If the black hole has no entropy of its own, the total visible entropy has decreased. That would violate the second law of thermodynamics, which says that the entropy of a closed system should not decrease. Bekenstein proposed that black holes must have entropy. The amount should increase when matter falls inside. More surprisingly, he argued that the entropy should be related to the area of the event horizon. This was unusual. For ordinary systems, the amount of information usually grows with volume. A larger room can hold more books than a smaller room. A larger computer memory can hold more data. We expect storage capacity to depend on how much space is available inside. A black hole appears to work differently. Its entropy depends on the area of its boundary, not the volume behind it. If the horizon becomes larger, the entropy increases. The interior volume does not play the expected role. At first, this was a suggestive idea rather than a complete result. Then Stephen Hawking studied quantum fields near a black hole and found that black holes should have a temperature. The calculation begins with the quantum vacuum. Empty space in quantum field theory is not completely inactive. Fields remain present even in their lowest energy states. Near an event horizon, the strong curvature of spacetime changes how different observers describe those fields. A distant observer sees particles being emitted from the region near the horizon. The black hole appears to radiate. This is now called Hawking radiation. The radiation is extremely weak for large black holes. A black hole with the mass of a star would have a temperature far below the temperature of the surrounding universe. It would absorb more energy than it emits. Detecting its Hawking radiation directly would be extraordinarily difficult. A smaller black hole would be warmer. As a black hole loses mass, its temperature rises and its radiation becomes stronger. The process accelerates. If nothing else falls in, the black hole may eventually evaporate. This result connected three areas of physics that had previously seemed separate. General relativity supplied the black hole and its horizon. Quantum theory produced the radiation. Thermodynamics described the temperature and the entropy. The connection was precise. Bekenstein had been correct that black hole entropy depends on horizon area. Hawking's work established the exact relationship. The result is now considered one of the strongest clues in the search for quantum gravity. It tells us that black holes must possess microscopic states. Temperature and entropy normally arise from hidden small-scale degrees of freedom. A gas has entropy because its molecules can be arranged in many ways. A solid has entropy because its atoms can vibrate and occupy many microscopic states. If a black hole has entropy, something beneath the classical geometry must account for it. General relativity does not tell us what those microscopic states are. From the outside, a stationary black hole can be described by only a few overall properties. It has mass, rotation, and electric charge. The detailed structure of everything that formed it seems to disappear. This is sometimes summarized by saying that black holes have no hair. The phrase means they do not display the fine details of their history. A black hole made from collapsing gas and a black hole made from collapsing books could look identical if their total mass, rotation and charge were the same. This is unfortunate for the books, though it would at least settle the question of overdue library fees. The entropy says that many hidden states must exist, even though the classical black hole looks simple. A theory of quantum gravity should explain what those states are and why their number produces an entropy based on area. String theory achieved an important success here. For certain idealized black holes, researchers were able to count microscopic arrangements of strings and branes. The number matched the entropy predicted from the horizon area. This did not solve every black hole problem. The black holes used in the calculation had special properties that made the mathematics manageable. Ordinary astrophysical black holes are more complicated. Even so, the results showed that a candidate quantum gravity theory could account for black hole entropy using real microscopic states. Loop quantum gravity has also produced calculations of black hole entropy. In that approach, the horizon is crossed by quantum links associated with discrete geometry. Different arrangements of those links contribute to the number of possible horizon states. Under suitable assumptions, the entropy again grows with area. The details differ, but both approaches support the idea that a black hole horizon contains information about quantum geometry. The smooth surface described by general relativity may hide a large number of microscopic configurations. Hawking radiation then creates the information problem. Imagine forming a black hole from matter in a known quantum state. The matter crosses the horizon. Much later, the black hole emits radiation and gradually shrinks. If the radiation is completely thermal, it carries information only about the black hole's temperature. It does not reveal the detailed state of the matter that fell inside. When the black hole disappears, the original information appears to have vanished. Quantum mechanics says this should not happen. The evolution of a closed quantum system preserves information. A state can become highly scrambled. Recovering it may be practically impossible. Still, the information remains in the complete pattern of the final state. Burning a book provides a useful comparison. The words become impossible to read. The pages turn to ash, smoke, heat, and light. In principle, however, the information has not been destroyed. It has been distributed among an enormous number of particles and correlations. Reconstructing the book would be beyond any realistic ability. But quantum theory says the detailed information still exists. Black hole evaporation appears different. If the outgoing radiation is exactly thermal, there may be no hidden correlations containing the original state. The evolution would change a complete quantum state into an incomplete statistical mixture. That would require a basic modification of quantum mechanics. For many years, physicists disagreed about which principle should be sacrificed. Hawking initially argued that information was truly lost. Others believed quantum theory must remain intact, and that the semi-classical calculation of radiation was missing something. The disagreement was serious because both sides were defending successful ideas. General relativity says the horizon blocks outward signals. Quantum mechanics says information cannot disappear. Hawking's calculation uses both theories in an approximate way and seems to produce a contradiction. One possible answer is that information escapes in the Hawking radiation. The radiation would not be perfectly thermal. It would contain extremely subtle correlations that encode everything that fell inside. This is now the view held by many physicists. Several developments in string theory and holography support it. The remaining problem is explaining how the information gets out without violating the smooth geometry predicted at the horizon. The process can be studied by tracking the entanglement between the black hole and its radiation. Early in the evaporation, each new piece of radiation appears entangled with a partner associated with the interior. The radiation outside becomes increasingly entangled with the black hole. If the black hole eventually disappears while information is preserved, this trend cannot continue forever. At some point, later radiation must begin carrying information about the earlier state. The total entanglement should rise, reach a maximum, and then fall as the black hole completes its evaporation. This expected pattern is called the Page curve, named after physicist Don Page. It provides a way to distinguish information preserving evaporation from permanent information loss. Recent theoretical calculations using methods inspired by quantum gravity have reproduced the expected Page curve in simplified models. The calculations include new, geometric contributions, sometimes described as islands. Part of what would normally be considered the black hole interior becomes associated with the radiation when its information content is calculated. This is a striking result. It suggests that the division between the inside of a black hole and the outside radiation is not as simple as classical geometry implies. Information that appears to be trapped inside may already be encoded in the radiation. The islands are not ordinary pieces of land floating in space. They are regions selected by a quantum calculation of entropy. Their appearance shows that geometry and information are connected in a way that classical reasoning misses. These results have strengthened the belief that information is preserved. They have not provided one universally accepted account of what an observer would physically experience near the horizon, or how the interior is constructed. The smooth horizon creates a sharp problem. According to general relativity, a person falling into a sufficiently large black hole should notice nothing special while crossing the event horizon. The local curvature there may be gentle. The observer should continue falling normally until stronger tidal effects develop deeper inside. Quantum information arguments can lead to a different conclusion. To preserve information, the outgoing radiation may need to be entangled with earlier radiation. At the same time, the usual smooth horizon requires each outgoing particle to be entangled with an interior partner. Quantum entanglement cannot be freely shared in both ways at once. A system that is fully entangled with one partner cannot also be fully entangled with another independent partner. This creates a conflict between information preservation, ordinary quantum field theory near the horizon, and the smooth passage predicted by general relativity. One proposed solution is the firewall. In this picture, the horizon is not smooth. An infalling observer encounters high-energy quantum effects and is destroyed at or near the boundary. This protects certain rules of quantum information, but violates the expectation from general relativity that nothing unusual occurs there. The firewall proposal caused intense debate because each alternative seemed to demand an uncomfortable sacrifice. Keep the horizon smooth and information may be lost. Preserve information in the obvious way, and the horizon may become violent. Change the structure of the interior, and ordinary ideas of locality may fail. Another proposal is black hole complementarity. It suggests that no single observer sees a contradiction. A distant observer can describe information as being stored and later released from the horizon. An infalling observer can describe passing through a smooth horizon. The two descriptions cannot be compared directly because the observers cannot exchange all their observations after the crossing. Complementarity works by allowing different descriptions of the same information without creating observable duplication. It is a subtle idea, and whether it resolves every version of the paradox remains debated. Some researchers argue that the interior is encoded in the outside degrees of freedom. The information is not copied into two independent places. The interior and exterior descriptions refer to the same underlying quantum data in different ways. This possibility leads naturally to holography. The holographic principle begins with the area law for black hole entropy. If the maximum amount of information in a region depends on its boundary area, then perhaps the physics inside the region can be completely described by information on that boundary. A familiar hologram is a flat surface that stores an image appearing three-dimensional. The physical principle is more general and does not require a visible image. It proposes an equivalence between a theory with gravity in a volume and a theory without gravity on the boundary of that volume. The strongest example comes from string theory. In a particular kind of curved spacetime, a gravitational theory in the interior is mathematically equivalent to a quantum field theory, defined on the boundary. This relationship is called a duality. The two descriptions look very different, but they contain the same information. An event described as a black hole in the gravitational theory corresponds to a thermal state in the boundary quantum theory. The boundary theory follows ordinary quantum rules and preserves information. If the two descriptions are exactly equivalent, then black hole evaporation in the gravitational description must also preserve information. This is one of the strongest arguments against permanent information loss. The boundary theory does not allow the information to disappear. Therefore, the gravitational description must contain a mechanism that returns it, even if that mechanism is difficult to see using classical space-time. The best understood holographic examples involve universes with properties different from our own. Their large-scale geometry has a particular form that makes the mathematical duality possible. Our observed universe does not appear to have that exact structure. Researchers are working to extend holographic ideas to more realistic cosmological settings. The complete version for our universe has not been established. Still, the known examples demonstrate something important. A quantum theory without gravity can fully describe a spacetime in which gravity is present. This suggests that gravity and spacetime may emerge from a deeper quantum system. The connection to entanglement makes this idea more precise. In holographic models, the geometry of the interior is closely related to patterns of quantum entanglement in the boundary theory. When the entanglement is changed, the interior geometry changes. If the entanglement is reduced enough, parts of the spacetime can separate. Space may therefore be held together by quantum entanglement. The statement is not merely a metaphor. In certain mathematical models, geometric distances and areas are directly connected to measures of entanglement. This raises a new way to think about location. Two regions may be close because the underlying quantum degrees of freedom are strongly connected. Distance could be a large-scale description of information relationships. A smooth interior would then emerge from a highly organized pattern of entanglement. The classical geometry seen by an observer would not be fundamental. It would be a useful description of the quantum information structure. This idea also appears in discussions of wormholes. A wormhole is a geometric connection between distant regions of space-time. In some theoretical models, a non-traversable wormhole is related to entanglement between two quantum systems. The two systems are connected in the quantum description, and the gravitational description represents that connection as a bridge. This relationship is sometimes summarized by saying that entanglement and wormholes may be two descriptions of the same underlying structure. It does not mean that every pair of entangled particles creates a tunnel through which a person can travel. The wormholes involved are generally not usable for ordinary transport, which is disappointing for anyone hoping to reduce the morning commute. The idea is valuable because it connects geometry with quantum information. What looks like a spatial bridge in one description looks like entanglement in another. Researchers have also used these ideas to study how information might escape from black holes. Quantum teleportation provides a useful comparison. In teleportation, the state of a quantum system can be transferred using entanglement and ordinary communication. The original state is not copied. It is reconstructed elsewhere through a process that preserves quantum information. Certain models of traversable wormholes have been shown to be mathematically related to quantum teleportation. Information appears to pass through a geometric shortcut, while the equivalent quantum description explains the process using entanglement and interactions. These models do not provide a practical method for traveling through astrophysical black holes. They do show that geometry, information transfer, and entanglement can describe the same process from different viewpoints. Black holes may also act as extremely efficient scramblers. When information falls into a black hole, it becomes mixed among the black hole's microscopic degrees of freedom very quickly. The information is not destroyed, but it becomes difficult to identify in any local part of the system. A stirred cup provides a simple comparison. Add a drop of milk and stir. At first, the milk occupies one visible region. Soon it is spread throughout the tea. The information about its original location has not vanished from the exact molecular state, but it has become distributed among countless motions and collisions. A black hole may scramble quantum information faster than almost any other physical system. This could explain why information seems lost even if it is eventually released. It returns in correlations spread throughout the radiation rather than as recognizable objects. A diary falling into a black hole would not later emerge as a slightly warm diary. Its information might be encoded across an enormous collection of radiation particles. Reading it would require measurements of impossible precision and control. Privacy would be maintained, though the method is excessive. The event horizon may therefore function less like a permanent prison and more like a powerful processing boundary. Information enters, becomes scrambled, and later appears in a radically transformed form. This view still leaves the interior to explain. If the information is encoded outside, what does the falling observer experience? Is the interior an independent place? Is it reconstructed from the external quantum state? Does it exist only relative to certain observers? Some recent ideas suggest that spacetime inside a black hole can be reconstructed using quantum error correction. Quantum error correcting codes protect information by spreading it across many physical components. The information remains recoverable even if some components are lost. Holographic models appear to use a similar structure. Information about a region in the interior can be encoded across different parts of the boundary. No single small boundary region contains the full message. The geometry is protected through a distributed quantum code. This helps explain how the same interior information can be represented in several overlapping ways without being copied. Different collections of boundary data can reconstruct it, much as a carefully designed code can recover a message after some data is damaged. The connection between spacetime and error correction was not expected from classical gravity. It emerged from efforts to understand black hole information. Once again, a contradiction produced a new clue. Black holes also raise questions about the smallest possible amount of information. The area law suggests there is a limit to how much information can fit inside a region. Trying to store more energy and information may cause the region to collapse into a larger black hole, increasing the boundary area. This means nature may not permit unlimited information density. A volume that appears continuous may contain only a finite number of physically distinguishable states. If so, spacetime cannot contain an independent degree of freedom at every mathematical point. A continuous geometric description includes infinitely many points, but the true quantum theory may have a finite information capacity for any finite region. This does not prove that space consists of a simple grid. The microscopic structure could be far more subtle. It does suggest that the continuum of general relativity may be an approximation. The boundary area provides the count, while the interior geometry emerges as a way of organizing the information. This reverses the usual assumption. We normally think the interior is fundamental, and the boundary records what happens there. Holography suggests the boundary description may be complete, while the interior is reconstructed. The idea remains difficult to apply to the real universe. We do not live in the best understood holographic space-time. Astrophysical black holes form, interact with matter, and exist in an expanding cosmos. A complete quantum description of them is still missing. Even so, the hidden clues are becoming clearer. Black hole temperature says quantum fields respond to horizons. Black hole entropy says geometry contains microscopic states. The area law says information capacity is tied to boundaries. The information paradox says classical spacetime cannot be the whole story. Holographic duality says gravity can emerge from a lower dimensional quantum theory. Entanglement calculations suggest the interior is encoded in the radiation. Error correction suggests spacetime is a protected form of quantum information. These clues come from different calculations, yet they point in a related direction. Space, gravity, and information may not be separate concepts. They may be different large-scale descriptions of one quantum structure. This does not mean physicists have solved quantum gravity. The strongest results often apply to simplified models. Important questions remain about realistic black holes, expanding universes, singularities, and the experience of observers. Different approaches interpret the clues in different ways. Some see support for string theory and holography. Others believe discrete geometry remains essential. Some expect spacetime to emerge from entanglement. Others think the final theory will include structures not yet understood. The clues narrow the possibilities without selecting one complete answer. They also change what a solution should look like. A successful theory may not begin by quantizing a smooth gravitational field in the ordinary way. It may need to explain how smooth geometry appears from information, entanglement, networks, strings, or another non-geometric foundation. The interior of a black hole may not be a simple region sitting behind a boundary. It may be a reconstruction from quantum data. The horizon may not be a passive edge. It may be where the relationship between geometry and information becomes visible. Hawking radiation may not be featureless heat. It may be the final carrier of a message scrambled beyond ordinary recognition. A theory that explains these features must still answer the questions raised earlier. It must recover Einstein's space-time at large scales. It must preserve the successful predictions of quantum physics. It must remove the uncontrolled infinities. It must describe the earliest universe and the deepest interiors of black holes. It must show why time, space, locality, and causality appear as stable features. Black holes have provided pieces of that answer, but the complete structure remains out of view. We can see the outline through entropy, radiation, holography, and entanglement. We can identify relationships that no classical theory predicted. We can build models in which space-time emerges and information survives. What we cannot yet do is place every clue inside one confirmed description of nature. The search has moved beyond asking whether gravity should be quantum. The evidence from black holes strongly suggests that it must be. The harder question is what kind of quantum theory can produce a universe with geometry, matter, time, and observers all at once, and why that theory appears to hide its basic rules so effectively behind the smooth space-time we experience. The harder question is what kind of quantum theory can produce a universe with geometry, matter, time, and observers all at once, and why that theory appears to hide its basic rules so effectively behind the smooth space-time we experience. At the moment, physics does not have one confirmed answer. It has clues, partial models, successful calculations, and several serious proposals. It has theories that explain certain black holes, theories that replace singularities with quantum structures, and theories in which space-time emerges from information. What it does not have is a single framework that has passed decisive experiments and shown that it describes the universe we actually inhabit. This is why quantum gravity remains one of the greatest unsolved problems in physics. The difficulty is not simply that the calculations are long. Physicists are quite familiar with long calculations. Some of them appear to regard several hundred pages of mathematics as a pleasant way to spend a weekend. The deeper difficulty is that the problem challenges the concepts used to build the calculation in the first place. Ordinary quantum theory assumes that events happen in space and develop over time. General relativity says that space and time are physical and change in response to matter and energy. A complete theory must describe quantum events without assuming a fixed stage, because the stage itself is one of the quantum objects. This means the final theory may not begin with space. It may not begin with time. It may not even begin with particles in the familiar sense. Those things could appear only after more basic elements organize themselves in the right way. The situation is not without precedent. Human beings once treated heat as a substance that flowed between objects. Later, heat was understood as the collective motion of particles. The smooth pressure of a gas turned out to arise from countless molecular collisions. A sound wave turned out to be organized motion in a material rather than a separate substance travelling on its own. In each case, the large-scale phenomenon remained real. Heat did not become imaginary when its microscopic explanation was discovered. Pressure did not stop pushing against the walls of a container. The deeper theory explained why the familiar description worked. Spacetime may have a similar relationship to quantum gravity. It could be real at the scale of planets, people, and laboratories, while not being fundamental at the smallest scale. Curvature may describe the collective behavior of a deeper quantum structure. Distance may emerge from patterns of connection. Time may emerge from change between parts of a system. Gravity may be the large-scale response of those relationships. This possibility changes how the search is conducted. Physicists are not only trying to quantize gravity, they're also trying to understand why geometry exists at all. A successful theory must explain why the universe appears to have three large directions of space and one direction of time. It must explain why time behaves differently from space. We can move in several spatial directions, but we experience time in one direction. We can choose to travel north or south. We cannot choose to spend tomorrow moving toward yesterday. The theory must also explain locality. In everyday physics, objects influence one another through nearby interactions. Signals do not normally leap across the universe without passing through the space between. Quantum entanglement creates correlations across distance, but it does not allow ordinary information to be sent instantly. General relativity protects causal order through the structure of spacetime. If spacetime emerges from a deeper network, locality must emerge with it. The underlying elements may not be arranged in ordinary space, so the familiar meaning of near and far cannot be assumed. The theory must show why certain interactions appear local, and why violations of locality are not obvious in daily life. It must explain causality as well. Causes appear before their effects. A glass falls before it breaks. A star collapses before a black hole forms. The alarm rings before someone decides to ignore it for another 9 minutes. At the deepest quantum level, the order of events may not always be fixed. Some theoretical processes allow several possible causal arrangements. Quantum gravity must show why the large-scale world settles into a reliable sequence. The direction of time creates another demand. Most basic physical laws do not strongly distinguish between past and future, yet our experience does. We remember the past and not the future. Heat spreads out. Objects break more easily than they rebuild themselves. Entropy increases. A complete theory may need to connect the arrow of time with the quantum state of the early universe. It may explain why the universe began in a condition that allowed entropy to grow. It may show that time and thermodynamics emerged together. For now, the reason the early universe had such an unusual degree of order remains one of the deepest questions in cosmology. The theory must also account for matter. A description of quantum geometry is not enough if it cannot produce electrons, light, atomic nuclei, and the forces already measured. The standard model of particle physics works extremely well. Any new framework must recover its successes rather than replacing them with vague possibilities. This creates a difficult balance. The final theory must be different enough to repair the failures of current physics, but familiar enough to reproduce everything current physics gets right. General relativity has survived tests involving planets, stars, gravitational waves, clocks, satellites, and black holes. Quantum theory has survived tests involving atoms, particles, materials, lasers, and entanglement. A successful theory of quantum gravity cannot casually damage these results. It must reduce to the existing theories in the conditions where they have already been confirmed. That requirement often guides researchers more strongly than imagination. Many possible theories are easy to invent. Very few produce general relativity at large scales, quantum field theory at low energies, and consistent behaviour at the smallest distances. The universe does not reward novelty on its own. A strange idea is not valuable merely because it is strange. It must explain known evidence, avoid contradictions, and lead to new predictions. Predictions are where the search becomes especially difficult. The strongest effects of quantum gravity are expected at a scale far smaller than anything current experiments can reach directly. Building a particle accelerator capable of exploring that scale would require an impossible amount of energy with present technology. Even a much larger machine would remain far away from the required conditions. This does not mean quantum gravity lies beyond science. It means physicists must find indirect routes. The early universe may provide one route. During its earlier stages, energy and curvature were much greater than they are today. Quantum gravitational effects may have influenced the patterns from which galaxies later formed. Those effects could have left traces in ancient light or in a background of gravitational waves. Researchers study the distribution of matter, the polarization of early radiation, and the statistics of cosmic structures. A distinctive pattern could support one class of theories over another. The challenge is that many ordinary cosmic processes can produce similar signals. The early universe does not come with clearly labelled evidence. Black holes provide another route. Observations of their collisions can test whether the resulting gravitational waves match general relativity. A small unexplained feature in the signal might point to new physics near the horizon or in the final object. So far, the observed signals have remained consistent with general relativity within the available precision. This is valuable even when no new effect appears. Every successful test restricts the ways quantum gravity can modify black holes at observable scales. The shadows of black holes offer another source of information. Telescopes can study the glowing matter and light surrounding the horizon. The images do not show the horizon directly, but they test the space-time geometry nearby. Future observations may become precise enough to reveal whether compact objects differ from the classical black holes predicted by Einstein. Again, ordinary astrophysics creates complications. Gas, magnetic fields, turbulence, and the motion of surrounding matter can hide subtle effects. A strange feature in an image does not immediately announce a new theory of space-time. It may announce that hot gas is difficult to understand, which astronomers were already aware of. Tiny laboratory experiments may provide a cleaner test. Several proposals aim to determine whether gravity can create entanglement between small masses. If two quantum objects become entangled only through their gravitational interaction, gravity must be capable of carrying quantum information. That would be strong evidence that a fully classical gravitational field is not enough. The experiment sounds modest compared with studying the beginning of the universe. It may involve small objects in a laboratory rather than collapsing stars. In practice, it is extraordinarily difficult. Gravity between small masses is extremely weak. Heat, vibration, electric fields, magnetic effects, and contact with the environment can destroy the quantum state or imitate the desired signal. Researchers must isolate the objects, preserve their quantum behavior, and measure an interaction far weaker than the surrounding noise. Success would not reveal whether strings, loops, causal sets, or another idea are correct. It would establish an important fact about what any correct theory must contain. Precision clocks may also help. Quantum clocks placed at slightly different heights experience different gravitational rates. Future experiments could explore situations where a clock follows more than one possible gravitational path. Such tests may reveal how quantum states and the passage of time interact. Other researchers search for evidence that space-time has a smaller scale. If space is discrete or fluctuating, light travelling across a great distance might accumulate a tiny distortion. Different energies of light might move at slightly different speeds. The sharp timing of distant cosmic events can test this idea. No confirmed effect has appeared, and observations have ruled out many simple versions. This does not eliminate every model of discrete spacetime. It shows that any microscopic structure must preserve ordinary relativity with impressive accuracy. The absence of obvious signals is itself a clue. If spacetime has quantum ingredients, they are very good at hiding. The large-scale world is smooth to a degree that any deeper theory must explain. This is sometimes called the problem of the classical limit. It is not enough to propose small quantum units of geometry. The theory must show how vast numbers of them produce a stable spacetime with predictable distances and durations. A pile of geometric pieces does not automatically become a universe. The pieces must organize into the right dimensions, the right causal structure, and the right gravitational behavior. They must allow matter to exist and interact. They must support stars, galaxies, chemistry, and observers capable of wondering where the pieces came from. String theory faces this requirement through its many possible solutions. The basic framework includes gravity, but it permits a large collection of ways for extra dimensions and fields to be arranged. Researchers must explain why our universe corresponds to one particular arrangement. Loop-based approaches face the problem from another side. They provide quantum states of geometry, but they must show how ordinary smooth space-time and familiar matter emerge in full detail. Holographic approaches offer powerful examples in special types of space-time, but the observed universe has different large-scale properties. Extending the same level of precision to a realistic, expanding cosmos remains difficult. Asymptotic safety must establish that the required high-energy behavior exists in the complete theory and derive clear predictions from it. Emergent gravity models must identify the deeper quantum system and explain why its collective behavior follows Einstein's theory. Every approach has strengths, and every approach has unfinished work. This does not mean they are equally likely to be correct. It means nature has not yet supplied enough evidence to choose decisively. Theories can still be compared through internal consistency and explanatory power. A proposal that removes singularities, preserves information, recovers known physics, and connects several puzzles is more promising than one that solves only a single calculation. Mathematical unity matters because a framework that explains several facts using one principle is less arbitrary. Yet elegance cannot replace evidence. The history of physics includes beautiful ideas that did not describe nature. It also includes theories that initially seemed awkward but were correct. The universe is not required to select the option that looks best on a blackboard. There may also be a problem with the assumption that one final theory will have a familiar form. Physicists often imagine a compact set of principles from which all known behavior can be derived. This hope has been successful before, but quantum gravity may not fit neatly into one traditional model. The complete description could involve several equivalent viewpoints. Holographic duality already shows that the same physics can have two very different descriptions. A gravitational universe in one framework can match a quantum theory without gravity in another. Neither description must be considered more real. They may be different languages for the same underlying structure. If this feature is general, quantum gravity may not provide one privileged picture. Strings, fields, geometry, and information could appear fundamental in different descriptions while remaining mathematically equivalent. Asking which one the universe is really made of might be like asking whether a journey is really a line on a map or a sequence of turns on a road. The useful answer depends on the description being used. This would not make reality subjective. The predictions would remain objective. Different formulations would agree on measurable outcomes even while organizing the explanation in different ways. The role of the observer may also need careful treatment. Quantum mechanics often describes probabilities for measurement outcomes. Cosmology attempts to describe the entire universe, including every observer and measuring device. There is no external observer available to perform the final measurement. A complete theory must explain how definite experiences arise within the quantum universe. It may use decoherence, relational states, branching histories, or a modification of quantum mechanics. The correct interpretation of quantum theory could become part of the solution, rather than a separate philosophical discussion. Gravity may even help explain why large objects appear classical. Different distributions of mass create different geometries. Some researchers suspect that this makes large quantum combinations unstable. Others believe ordinary environmental decoherence is sufficient. Future experiments with larger quantum objects may test these possibilities. If standard quantum behavior continues without deviation, gravity-induced collapse models will become more restricted. If a new loss of coherence appears and cannot be explained by the environment, it could transform both quantum theory and gravity. The problem therefore reaches beyond black holes and the early universe. It touches the question of why everyday reality has definite objects at all. For now, the smooth world remains an excellent approximation. The floor holds its shape. Clocks advance reliably. Light travels through space-time in predictable ways. The quantum uncertainty beneath matter does not cause the room to blur between several visible arrangements. A final theory must explain this reliability. It must show why the strange foundation produces such an ordinary surface. Perhaps space is made from quantum connections. Perhaps gravity is the statistical behavior of information. Perhaps strings provide the underlying objects. Perhaps geometry comes in discrete units. Perhaps the correct theory has already been partly discovered, but not fully understood. Perhaps every current approach is missing one simple principle. Science does not yet know. That answer can feel unsatisfying because we are used to scientific stories ending with the discovery. A problem is introduced, an experiment is performed, and the correct theory arrives before the final page. Real research does not follow that structure. The most important questions can remain open for generations. The lack of a final answer does not mean the search has failed. Quantum gravity has already changed the way physicists think about black holes, information, entropy, and space-time. It has produced new mathematics and revealed connections between theories that once appeared unrelated. The idea that a boundary can describe an interior came from studying black hole entropy. The connection between geometry and entanglement grew from the information paradox. Quantum error correction became relevant to the structure of space-time. Gravitational questions led to new insights about quantum many-body systems. A solution may emerge from these connections rather than from one dramatic experiment. Several ideas may slowly converge until a common structure becomes visible. An observation may then confirm what the mathematics has been suggesting. It could also happen in the opposite order. A precise experiment may reveal a small effect that none of the leading theories predicted. The correct framework might begin with that unexplained result. Either path would change our understanding of the universe. A confirmed theory of quantum gravity could tell us what replaces the singularity inside a black hole. It could explain whether another region exists beyond the classical endpoint, whether collapse ends in a quantum state, or whether the interior is encoded entirely in external information. It could describe the earliest meaningful stage of the universe. We might learn whether there was a beginning, a bounce, a transition, or a process for which the word before has no physical use. It could reveal whether space and time are fundamental. We may discover a smallest unit of geometry, or find that distance arises from entanglement. Time might turn out to be a relationship between changing systems rather than a universal background. It could unify gravity with the other forces or explain why gravity is different. It could show why the constants and particles of nature have their observed properties. It might even reveal that several things now treated as separate are expressions of one structure. There is no guarantee that every question will be answered at once. A theory can be correct while leaving difficult problems for later. General relativity did not explain quantum particles. Quantum mechanics did not explain gravity. The next framework may uncover a deeper layer while exposing new mysteries beneath it. That is usually how science progresses. Each successful explanation changes the questions. Newton explained motion and gravity, then relativity changed the meaning of both. Quantum theory explained atoms, then raised questions about measurement and reality. Black hole physics connected gravity with temperature, then created the information paradox. Holography protected information, then suggested that space itself may be encoded. The search does not move toward a point where nothing remains unknown. It moves toward better questions supported by more accurate theories. Quantum gravity is unusual because the object being investigated includes the structure used to investigate everything else. We use clocks to measure change, rulers to measure distance, and coordinates to locate events. The final theory must explain clocks, rulers, distance, and location using principles that do not assume them from the beginning. This is one reason progress is slow. Our language and intuition were built inside space-time. Trying to imagine what lies beneath space-time is difficult because every familiar image already places objects somewhere and describes them changing over time. A network is usually pictured in space. A string is pictured as having a length. A process is pictured as happening in time. These images may help, but they quietly reintroduce the concepts the theory is supposed to derive. Mathematics allows researchers to move beyond ordinary pictures. It can describe relationships without placing them inside a familiar room. The final framework may therefore be easier to calculate than to visualize. That would not be unusual. No one directly sees curved four-dimensional space-time, yet general relativity predicts measurable effects. No one sees a quantum state, yet its probabilities guide experiments. Physical understanding does not always require a simple mental image. It requires a consistent structure connected to observation. Until that structure is confirmed, quantum gravity remains the theory the universe is still keeping secret. The secret is not hidden because nature has made a decision to be difficult. It is hidden by scale, energy, and the limits of present experiments. It appears only where our most successful descriptions are pushed beyond their ordinary range. We find its traces near horizons, in singularities, in the area of black holes, in the preservation of information, and in the possibility that space-time emerges from entanglement. We see enough to know that the current picture is incomplete, but not enough to identify the final one. That may be the most honest place to end our journey. Not with a completed answer, but with a clear view of the problem. General relativity tells us that gravity is the changing geometry of space and time. Quantum physics tells us that the smallest parts of nature exist through probabilities, fluctuations, and entanglement. Black holes tell us that geometry has temperature and information. Holography tells us that an interior can be encoded on a boundary. Every clue suggests that space, time, matter, and information are connected more deeply than our present theories can explain. Somewhere inside that connection is the missing theory. Perhaps one of the current proposals is already close. Perhaps a future experiment will reveal the correct direction. Perhaps a student listening tonight will one day notice the assumption everyone else overlooked. For now, the problem remains open, and that is not a reason for disappointment. It is an invitation to continue thinking. If you have made it this far, you're now a little closer to the edge of modern physics than when we began. The room around you has not changed very much. Gravity still keeps everything in place. The atoms nearby continue following quantum rules. Space remains smooth, time continues to pass, and the disagreement beneath it all stays hidden from ordinary experience. Wherever you are listening from tonight, take a moment to notice that you are part of the same universe physicists are trying to understand. The matter in your body is quantum. The ground beneath you curves space-time. Every clock nearby follows relativity, even if the difference is far too small to see. If this long journey through the unfinished side of physics has helped you relax, think, or simply look at the universe a little differently, you can give the video a like and subscribe to Physics with William. It helps this quiet place continue exploring the questions that do not yet have tidy answers. There will be more theories, more observations, more arguments, and probably more black holes. One day, there may also be a result that brings the pieces together. Until then, the universe keeps its answer carefully hidden, while leaving just enough clues for us to continue looking. Sleep well, fellow traveller, and let gravity hold the world in place while the quantum details take care of themselves.